Welcome to this third scientific meeting about battery-based energy storage systems organized by Mondragon Universitatea. Here, we will have with us some of the best researchers in this field today, and we will cover some of the hot topics about energy storage system modeling and control. We will cover from the state of the art to the very last physics-based models, and also they will give us their point of view about these models and about the application of these models to the industry. So, to start the day, we will check the agenda that we will follow. So, first of all, we will start with Professor Jorge Varela Barreras, and he will talk to us about the state of the art of battery management systems for electromobility. He is an expert on this field. He works in the industry in the CITAG, and he works as well in the academy in the Universitat Politécnica de Catalunya. After this, our colleagues from University of Colorado, Colorado Springs, Dr. Plett and Dr. Scott Trimboli will talk to us about the physics-based models, first about the modeling itself, and after about the control of these models. And after this, we will have here our brand new doctors, Dr. Iker Lopetegui and Dr. Xavier Torrensoro, that will cover all the research that we perform here at the university. So you will have the chance to see what we do here. And finally, Dr. Eric Scholz from Aalborg University will talk to us about the battery state of health estimation in real life conditions. Okay, so now here we have with us Dr. Jorge Varela. Jorge has 15 years of research and development experience in batteries, battery management systems, and their application in electric vehicles and renewables. He holds 2 master's degrees in electrical engineering from the University of Vigo and in power electronics and drives from Aalborg University, and a PhD degree also from Aalborg. Currently, Jorge works in academia, as I said, at Universitat Politécnica de Catalunya and in industry at CETAG and Econ. Previously, he was a fellow in the Faraday Institution and postdoc in the Imperial College London and in the University of Oxford. He has been awarded a Maria Zambrano Fellowship at Universitat Politécnica de Catalunya and an honorary research fellowship at Imperial College London. He has been involved in more than 15 research and development projects with a combined budget over 70 million euros, and he has published a lot of papers, more than 15 papers, 19 conference papers, and 2 books, receiving more than 8,000 citations. So, Jorge, please, the floor is yours.
Thank you very much. Well, first of all, thank you for your kind invitation. It's a pleasure to be here. I don't know if there are 2 microphones working right now. If I approach, okay? Now it's good. You can hear me, right? Okay? Okay. Well, it's a great pleasure to be here today. Special thanks to Eric Arayalde and Unai Iraola for the organization of the event. Well, my task here today is to talk about the state of the art of battery management systems in electromobility. But this is a topic that I like very much. I've been working in this already for many years, and I can tell you that it's quite difficult to explain this in just 40 minutes. So I'll do my best, okay? I have to summarize. So basically, this is what I decided to bring as contents for today. I will give my own definition of what is a battery management system, because I would say that there is not a standard definition that is really nice. I will explain why a battery management system is actually needed in this space, what are the basic functions, and also I will try to give you an idea of what has been the evolution of these functions where are we today, where are we heading, and also I will try to explain how the BMS is integrated in the battery pack and the vehicle. But again, as I said, this has to be short. So this is a definition that I think is precise enough and not too long. So a battery management system, in my view, can be seen as a system that integrates hardware and software that is used to monitor and control operation of a battery, typically lithium-ion. This is what is being used in almost all the electric vehicles today, and manage communications and data. The BMS is optimized to improve battery system safety, usability, reliability, compliance, performance, and lifetime. I will talk a bit more about this. And every BMS works in a certain context of application, in this case, electromobility. So let's try to go in a bit more detail on each aspect of this definition. So why do electric vehicles require a BMS? Okay? This is the easy answer, because they use lithium-ion batteries. Okay, thank you very much. Okay, I will reformulate the question. Why do lithium-ion battery power electric vehicles require a BMS? Okay, probably this is a better question. And this is the short answer. We need a BMS to ensure safety, usability, reliability, performance, lifetime, and compliance. Probably I could add some stuff more, but we just have 40 minutes, okay? Let's go into a bit more detail again. So about safety. So lithium-ion batteries, they are prone to reduce lifetime and or catastrophic failure when operated outside certain safe operating area. This is an area of operation limited by voltages, currents, temperatures, and we can say also state of charge, in a certain combination. If you operate outside this area, you start having problems. The BMS contributes to keep the battery operation within this SOA, okay? In a nutshell, this is what the BMS is doing regarding safety. Also, BMS, advanced BMS, smart BMS can also do a lot of things related with faults. So it's able to diagnose and prognose faults and also control faults in different ways. Also, this is also related with safety, okay? And also it's doing some isolation monitoring. So if there is a problem in high voltage isolation, the BMS also helps with that. Regarding usability, okay, it's a big challenge to make a battery electric vehicle as usable or more usable than an internal combustion engine vehicle. Basically, you need at least a fuel gas. This means, in battery terms, state of charge estimation. You need a large and predictable range. You need capability for rapid refueling, in battery terms, recharging, at any station. So you need also compatibility with different charging stations. Well, we will not achieve this soon because there are different charging standards and protocols depending on which geographical region you are. So it's different in the US, it's different in Japan, in China, in Europe, but people usually do not drive from China to the US, right? Or from Europe to the US. So at least within a geographical region, the idea is that it should be compatible. In theory, it is more compatible than in reality. We are still working on that, okay? And also, it's important to communicate, as I said before, failure and also emergency. Well, the BMS contributes to all of that, okay? It's not the BMS the only system that contributes to that, but it's a key system for that. When we talk about reliability, okay, we have the safety part, I talked before already. It's part of being reliable, a product. We have the part of user satisfaction. Well, if my car is broken down all the time, I'm not very satisfied with the car. So this is part of being usable. Also, the economic part is important, okay? If I cannot use my car, if I have to go to maintenance all the time, this costs money. And then the compliance part. I will talk a little bit more about compliance in a while. So, just to give you an idea, these are the most common problems, most common reliability issues in battery electric vehicles. Battery degradation. The degradation is happening faster than it should, and the battery doesn't last until the end of life of the vehicle, which, depending on the geographical region, can be also very different. Nowadays, in Europe, particularly in Spain, we are using cars for more years. Also, there is a lot of second-hand market. Well, this is a challenge for electric vehicles. Range drops at extreme temperatures. So at low temperatures, battery capacity drops, but also you have all the heating and cooling. Well, at low temperatures, it's mainly heating. At high temperatures, it's also cooling. This is energy intensive. Then we have a problem that is not only for electric vehicles, but for all vehicles, electronics and control failures. This is one of the most common reliability problems in any kind of vehicle. And then we have also noise and sealing problems, or tightness, it can also be called. So the BMS plays a key role in controlling battery degradation, we know this. Thermal management, well, sometimes the thermal management system is considered as another system, sometimes it's considered as part of the BMS. What is clear is that there is a control component that is part of the BMS. Depending on the scientist or the engineer, they may consider it part of the whole thermal management system, part of the BMS or not. Well, it doesn't matter. Although it's also true that due to its own complexity, and also it's a complexity that is growing, both in terms of software and hardware, the BMS can be also a source of failures. There are some studies that are quite interesting about this. This is also something that we are working on. So how to make BMS more complex, with more advanced and intelligent features, but at the same time keeping reliability. We also have to talk about performance, of course. And this is the typical metric that everybody thinks, firstly. Like, what is the battery and, at the end of the day, the vehicle performance in terms of power and energy? So in terms of acceleration and range, because power translates to acceleration, energy translates to range. So battery performance depends on temperature. It's an electrochemical system. So electrochemical systems and temperature are tightly coupled. A state of charge, a state of health. A state of health is a measure of how much degradation there has been in the battery in terms of changes in capacity and internal resistance. A state of available power, how much power can the battery deliver, and auxiliary systems consumption. Well, usually auxiliary systems consumption is not considered, but actually electric vehicles and all vehicles in general are having more and more electronics. And the auxiliary power consumption is increasing. Also, there are more electronic and electric equipment all around to make your life more comfortable. You have all this infotainment. We want a huge screen. Well, all this stuff is increasing auxiliary power system consumption up to a level that we cannot just neglect it. Okay. Well, the BMS monitor battery states. The BMS control the thermal management system, which, as I said, is energy intensive. Particularly if you are, for example, preheating a battery. If your car has been parked for a long time in low temperatures, and you have a huge battery pack, and you need to drive your car, in many cases you need to preheat the battery pack, also if you want to do charging. Well, to heat up a battery pack that is weighing several hundred kilograms is something that is energy intensive. So the BMS works in symbiosis with the rest of the vehicle, okay? And now, if we talk about lifetime, well, we know that batteries degrade over time. All of us have experience with batteries degrading, and our experience comes from consumer electronics. But, well, the same happened in electric vehicles, especially at the beginning. So electric vehicles leverage all this experience gained from consumer electronics, and also they got this, the industry was there, all this experience with manufacturing batteries and developing new materials for cathodes, and, well, in one word, optimizing the battery manufacturing and these economies of scale that could be built because there was already a big consumer electronics market. This has been really important for batteries, battery management systems. Right now, the electric vehicle market is much, much bigger than the consumer electronics market and will be even bigger. And it's just because, well, maybe in one car you have the equivalent of 1,000 batteries of a phone, okay? Well, so important factors for battery lifetime and degradation, the rate of degradation, how fast degradation happens are temperature, state of charge, and current. Current both considering the direction of the current, so if you are charging or discharging, and the magnitude of the current, okay? And these factors interact, so you have to consider them together, not isolated. In addition, operation, as I said before, operation outside the safe operating area leads to accelerated degradation. So what is the BMS role? The BMS has direct influence in the management of all these quantities and also in keeping the operation of the battery within this SOA. Okay, and now a topic that a few years ago I didn't think it was that important, but then I started working in automotive industry. So for automotive industry and for industry in general, compliance is of utmost importance. So if you can have legal issues, and also it's very much related with delivering a high quality product that keeps the user, that keeps high level of satisfaction for the user. So for an electric vehicle to be marketable, so you can sell it, not today, but for many years, it has to be safe, usable, reliable, performant and durable, and ecological. And there could be other things, but these are basic points. To achieve that, there are a great number of regulations and standards, which goal is to guarantee a compliant product. This involves a lot of testing, performance testing, durability testing, safety testing, and so on. And the BMS, of course, is part of the system. So you need a BMS to get the battery modules and the battery packs and the battery systems operating, so you can conduct all these tests and then at the end of the day be compliant. There are also some specific standards regarding the BMS. In particular, we have seen in the last years a lot of importance given to some automotive safety standards that involves many changes in the software and hardware of the BMS, and this is the famous ISO 26262 and this AC level C and D and so on. I cannot go into more detail. We can speak later about this if you want during the coffee break. Okay, so let's go to another point in the BMS definition that I have given before. A BMS is used to monitor and control operation of a battery, typically a lithium-ion battery, and manage data and communications. Okay, let's go in a bit more detail on this sentence. So the question now is, what are the basic functions of a BMS in electromobility? Okay, and I summarize in this: monitoring, control, communication, and data management. And when talking about monitoring, basically what do we have to monitor is voltage at pack and cell level. Current today is mainly done at pack level only. Temperature, some surface temperatures of some cells, or also components of the electronics, and also components of the heating and cooling system. It's not always required to directly measure temperatures at the cell level or on the surface of the cells. You can do it also indirectly through, for example, the liquid that is used in the cooling heating system, okay? Isolation, so to monitor isolation, to ensure that you don't have problems with the high voltage battery. The high voltage battery in an electric vehicle is a floating system, so neither the positive or the negative terminal is connected to the chassis. It's a floating system. You can detect single faults using a ground isolation monitor, and therefore, in that way, you can avoid the big problem when you have two faults, and then you close the circuit, and then you can have a short, and also you can have some problems with health and safety. Interlocks. So when you are charging and you connect the cable of the charger, well, you don't want to disconnect and touch the pins and then get electrocuted. So there are some interlocks to ensure that. And also state and fault estimation. Well, now this is just a line, but there is so much literature around state and fault estimation. I will talk more about this later. Okay, control. What do you have to control? From a high-level perspective, well, operation within the SOA, power and energy management, up to a certain level, depends on the system. Thermal management, cell balancing, controlling relays and switches. Usually you have a connection box that allows you to connect the battery to the onboard or the offboard charger and the powertrain, so the inverter or inverters and the motor, and also connection to the heating cooling system, because it's so energy intensive that needs dedicated connection and protection with fuses and relays. Also include the word switches there, because sometimes there are also switches. Lately, we have seen something new. They are called pyro switches. This is in case of emergency, by pyrotechnic methods, you can open a switch. You can only use this once. You have to control the charging process, and there are different ways to do it. There is what we call the dump charging. It's very basic charging method, which basically tries to charge the battery as fast as possible using all the power that is available from the charger and the grid, or all the power that the battery can take. And then we have the smart charging algorithms that try to do something else, something extra. Now we are moving into smart charging. We have already done what is called scheduled charging, and we are starting to do what is called dynamic charging with also bidirectional power capabilities. But this is still happening right now. Also, regarding control, you have to prevent, detect, and mitigate faults. You need a system that is fault tolerant, and you need a system that fails in a safe way. So you don't want to be driving your car in the highway and then, oh, battery failure, I'm out of control. Doesn't sound very nice, right? And also, you don't want to go to the workshop each time you have a small problem, for example, with a sensor. So you need also redundancy in components and so on to ensure fault tolerance. Sometimes also there are more than one microcontroller. This is becoming more common on a BMS. So if one fails, the other can do basic things. So you can fail safe and achieve some level of fault tolerant operation. Regarding communication and data management, well, we could talk a lot about this because there are many different ways to communicate data. There are a lot of protocols, a lot of standards. But basically, I will just summarize like this. You need communications within the BMS. The most common architecture these days is not centralized. It's master and slave. So you have a master board and some slave boards. They have to communicate to each other. Also, isolation is needed because you have some high voltage measurements and you have some also low voltage system. Then you need also communication outside the BMS, but inside the vehicle. So the BMS communicates with other components of the vehicle, including electronic systems like the vehicle central unit. And sometimes, well, it's not easy to say, okay, what is the system that is, for example, controlling the charging process? Is it the BMS, or is actually the vehicle central unit, or is another intermediate electronic unit? Well, because actually this is not defined in the standard, so it can be implemented in different ways. And also you need communication from the vehicle to other places. The basic example is the charger. And then the charger is also communicating with many other places. Well, communication in charging, well, this is also a complex topic. You need communication also to the cloud. This is now becoming the new standard. And you need that for also software updates and data exchange, telemetry. You send data, some analysis is done in the cloud, and you get some valuable metrics that can help you to optimize the operation of the battery. Okay, if I make a basic drawing about how the BMS looks like, we will have here the lithium-ion battery pack. This is the BMS. And these are other systems of the vehicle, the fuse and switch box, sometimes called connection box or distribution box, the charger, which can be on board or off board, and the powertrain, so the inverters and the motors, or inverter and motor, depending. There are many configurations possible. Here you have electrical connections. Here you have heat exchange. This is the heating and cooling system. There are many different configurations for the heating and cooling system, and different components can be interconnected. So the power electronics, the motor, and the battery can be interconnected. Also, the cabin can be interconnected. And then here we have the BMS, and the BMS is doing sensing in these components, also doing sensing at cell level and module level and pack level. There is also a low electric power link, mainly for balancing. Usually it's passive balancing, what we have today for light-duty electric vehicles. For heavy-duty electric vehicles, we have already vehicles with active balancing as well. So the BMS is doing here balancing, monitoring, data management. So we have here control loops and data. Here we have logging and telemetry, and the vehicle central unit, also called control central unit, with wireless communication, for example, to the cloud, could be to other vehicles, to a building. And here we have the battery management algorithms, so the high-level application layer with all these fancy algorithms. Okay, if we talk about monitoring, and we go in a bit more detail, we can differentiate between two big functions. There are different ways to classify this. I like this classification. It's my own. I like this because it's simple and it works. So basically, you have sensing, what I call sensing, and this is when you make a direct measurement of physical quantities or states, mainly voltage, current, temperature. Sometimes resistance and impedance can be included in this classification. Isolation, relay switches, and fuses. So you can detect if there is a malfunction in a relay of a switch or a fuse as well. And then you have estimation. And estimation is about inferring the actual or future state or faults of a battery indirectly from available data, often through some kind of models, or of course you need some kind of algorithms. Okay, and when we talk about monitoring and estimation, we can say again that we estimate states and faults. Regarding nomenclature, it's also possible to differentiate between estimation, what is so-called diagnosis, when you want to know the state the state or if there is any fault right now, at present time, or in the future. Then we talk about prediction and prognosis. In general, I prefer to use the word estimation to talk about altogether, just because it's more simple. But please be aware of that. Initially, these algorithms were focused on state diagnosis, particularly state of charge. Well, in hybrid electric vehicles, there were also particular interest on state of available power, but for battery electric vehicles, basically state of charge. But this evolved continuously to diagnosis and prognosis of more states, including state of health and state of available power and faults. I will talk a bit more about this, about the evolution of this. And regarding control, well, you can summarize in these 6 areas: relays and switches, thermal management, charging, derating, which is about limiting the charging and discharging current to keep the battery within a certain operating area, not just a safe operating area, but an area that can be interesting, for example, in terms of minimizing degradation. Energy management, or we can say also power and energy management, and balancing. And this is, well, the slide that summarizes the evolution of the functions. I made this slide yesterday because I realized, okay, now I have 15 or 20 more slides, but I don't have more time, right? So, so I said, okay, Jorge, let's do it. Let's put all this information in one slide. Later you can tell me if you like it or not. Maybe there is too much information here, but let's try. At the beginning of time with electric vehicles, BMS were very simple. We can call this the first generation. Now we are, let's say, in the second generation, moving into the third generation with what I call intelligent BMS. You can also call smart BMS. To be honest, I hate this word because now everything is smart, everything is intelligent. I think it's a commercial word, but well, somehow I need to name this with one single word. So I chose intelligent. Okay, my fault. Okay, so at the beginning, you have BMS with very basic sensing, passive balancing. This is, in most of the cases, still today. Basic state of charge estimation based on column counting. Heuristic-based derating, so some basic rules to keep the battery operation within a safe operating area. And we have what is called dumb charging. So basically, you try to charge with as much power as possible, as much power as it is available from the charger, the grid, and the maximum power that the battery can accept. Here we are today in all electric vehicles in the market, and we are moving into this. So some electric vehicles in the market already incorporate aspects of intelligent BMS. And ideally, in the future, near future, all vehicles will have this kind of intelligent BMS. So with advanced BMS, you have redundant sensors. So mainly because of this need for safety, you need these fault-tolerant systems, redundancy in sensors. So you can, for example, measure cell voltages with more than one IC. So if one fails, okay, you can still measure with the other. ICs are quite cheap for that purpose. Active balancing, okay. Well, I included it here, but the standard is still passive balancing, but we see some BMS with active balancing, particularly in heavy-duty applications. Now we have some basic fault estimation. Of course, the most basic fault estimation could be, for example, you measure all the cell voltages, you sum up the cell voltages, you measure the pack voltage, and you compare. If the basic math doesn't work, you have a problem. But this is also done by simple BMS. When I talk about basic fault estimation, it's a little bit more. Model-based state estimation here, with a lot of work in this area, a lot of work with Kalman filters, for example. Thermal management, the first battery systems were small battery packs, usually air-cooled. Then we moved to larger battery systems, and also with fast charging capability or faster charging capability. The thermal management system became more complex and basically liquid-based. And then also this scheduled charging, this is smart charging related with, okay, I don't want to use the maximum charging power from the beginning. I can wait, and depending on, for example, what is the cost of electricity or what are the power needs of my house, I can decide, okay, I will delay charging. In this case, with scheduled charging and dump charging, is the BMS the one that sets the reference set point for the charger. But in the next generation, when we have what is called dynamic charging, and also include here vehicle to everything, it's not the BMS anymore, the system that is setting the set point reference for the charger. It's coming from outside. And it's taking into account the integration of the electric vehicle and the charger within the network. Okay. In intelligent systems, we have smart sensing. Well, sometimes there is some smart sensing also in advanced systems, but it will become a commonplace in intelligent systems, and it's becoming a commonplace in intelligent systems right now. This is already happening, okay? So, for example, you only measure temperature in some points, but if you have a nice battery thermal model, you can infer temperatures in all the cells of the pack and also at the cells. This is important, particularly for fast charging at relatively low temperatures or low temperatures, okay? Because you want to avoid a phenomenon called lithium plating. And for that, temperature and current level are very important, and the distribution of temperature within the cell is very important. Smart balancing. Well, you can not only do active balancing, but you can, active balancing is about not dissipating power, but actually moving power from one cell to another, or one cell to the module or the pack and then back. A smart balancing is about adding more control objectives to the balancing circuit. You can have not only voltage or state of charge balancing, but you can have a state of available power balancing, or you can have temperature balancing, or you can also have battery degradation balancing. So if some cells or modules are degrading faster than others, you can, additional electronics, balance this performance and balance these metrics. Okay, smart balancing is not happening right now. It's adding a lot of complexity, cost, and there are some reliability issues. But in research, we are working on smart balancing things, okay? Then we have fault control. So it's not about only estimating faults, but it's about controlling them actively, mitigating the fault. Then we have also state and fault estimation, but not only model-based, but also using artificial intelligence. And now the models are not only equivalent circuit models and some kind of empirical or semi-empirical models. We also have physics-based models. And energy management and derating, taking into account degradation. This is becoming a thing. There are many vehicles already have these features, but it will be even more common in all different aspects of operation. And this is a big thing, edge and cloud BMS. So you have the electronics on the vehicle, but you have also the cloud, and the system is sending information there, and some state estimation, fault estimation is happening over there. Okay, and today there will be some lectures here providing more information about different aspects like artificial intelligence and model-based state and fault estimation. Professor Eric Solf is going to talk about this in the context of state of health estimation. Also, practical physics-based models. Professor Trimboli and Professor Plate are going to talk about this. Our practical physics-based models Iker, one of the new PhD students, is going to talk about this. And also degradation-aware energy management, Xavier Dorronsor is going to talk about this. So you can see at a glance what is going to happen today. How is going? I have to finish, right? Yeah, 5 minutes. Okay. My phone doesn't have battery. 5 minutes. Okay. Small problem. Okay. Just very quickly, well, I will not talk about models because some people will talk about models. But very, very briefly. Okay. We can make this overall classification: electrochemical models, semi-empirical models, data-driven models, and we can say, okay, in terms of applicability, this is what is happening. Easy to apply, more difficult, much more difficult. This is why there is a lot of work with electrochemical models. About model complexity, less complex, empirical or semi-empirical. Data-driven model, the complexity doesn't come from the model itself, but from the amount of data that you need to train the model. Physical, chemical knowledge, with electrochemical models, you need more knowledge. With data-driven, less. So this is like a black box approach, gray box approach, white box approach. Regarding experimental data requirement, well, with data-driven models, you need a lot of data. Also, with electrochemical models, actually, you need quite a lot of data because you need a lot of, ideally, the idea is in the future, you will not need that much, but nowadays, you need also a lot of empirical data similar to the one that you use for semi-empirical models. Hopefully, this will improve. Regarding model accuracy, in general, we would say that semi-empirical models are providing the best result in the field right now, but in research, there is a lot of work to improve that, so electrochemical models and data-driven models can get more accuracy. And regarding computational effort, well, electrochemical models are the winners. There are a lot of partial derivatives, there are also a lot of variables. Well, the equations are complex. This is also why there is a lot of work in this area in simplifying mathematically the models. Okay. And yes, very quickly, the BMS is a system that integrates hardware and software. So at the beginning, with hybrid and plug-in hybrid systems for 200 volts, today 400 volts, in the future 800 volts. We need to increase voltage. We want to increase power. And this is a requirement for fast charging and ultra-fast charging. But today, very few companies are providing 800 volts. And some of them, Porsche, Kia, and Hyundai, and Porsche started with 800 and came back to 400 in some models. It's difficult to change that. Regarding the architecture, this is a typical master-slave architecture. The master is doing high voltage sensing, voltage and current at pack level, isolation, relays, interlocks. Here you have the algorithms for estimation, control, and data management. And here you have communication from the master to the slaves, the electric vehicle, and externally, for example, the cloud, or the charger directly or indirectly through other electronic cards. Then you have, at the slave level, the cell voltage and module temperatures. Then you have passive balancing and the communication master-slave. This is typical structure of all the BMS nowadays. And where is the BMS located? Well, typically, all the electric vehicles today have this kind of modular battery pack configuration, although it's true that we are seeing these cell-to-pack or cell-to-chassis systems, but this is not commonplace yet. Most of the vehicles have modular platforms, and the investment to develop these platforms have been huge from the automotive industry, so this is not going to change very soon. So you have some boxes, one with thermal management things, one with battery management things, and another one with this fuse and switch box or connection box or distribution unit. Here are modules. These orange cables are interconnections, electrical interconnections between modules. You can have the slave placed in different places in the module. This is a module made of prismatic cells, as an example. In this case, we have a decentralized BMS, so one electronic unit per cell. but this is not the most common configuration. It increases cost and complexity. Most common thing is this kind of configuration, one slave board per module, and the master is in this box. So, in conclusion, remember, a battery management system is a system that integrates hardware and software used to monitor and control operation of a battery, typically lithium-ion, and manage data and communications, optimized to improve battery systems safety, usability, reliability, compliance, performance, and lifetime in a certain context of application, in the case of today's lecture, electromobility. And that's all. Thank you very much.
So
I have spoken too much, I'm sorry.
no, don't worry, it's okay.
I'm very Spanish. You know?
So thank you very much, Jorge. Now we have some minutes for questions and comments. So if any of the attendees have any question, something to say, that you have the chance now to talk to Jorge. And also, if you are online, you have the chance to ask questions via the chat, and our colleagues will read them. Yeah. Here you have.
Hello, Jorge. Thank you for your presentation. You mentioned a couple of times about active balancing.
Yes.
Could you explain a little bit more why in heavy duty you see this active balancing option and not in other kind of vehicles? Is it about the number of cells, or why do you think that this is being in this kind of vehicles?
Yeah, it is because of the size of the pack. At the end of the day, well, you have more chances to have, statistically, to have a cell that is creating problems in a very large pack that is all interconnected. So, yes, also in heavy duty, it's common to see also higher voltages. So it's not only that you have a larger pack, potentially with more cells. There are more cells of group of cells in parallel connected in series. So this is increasing the probability of having a problem. And the problems with balancing are related with also cell discharge and also uneven temperature distribution, state of charge, and so on. If you want to fast charge a truck, also, well, it is a big thing, and the investment is also huge. If you are going to operate fleets, you want to use this effectively. So if you have to do a lot of balancing in a truck, this is a problem because it reduces the effectiveness of charging. So you can find several reasons for that. But the kind of active balancing we have seen is quite simple. So it's not something really fancy. The current levels are quite low. So the things that we see in academic papers are not yet happening with high levels of balancing and so on. But I'm a big fan of this. I've been working a lot in academia, doing things about this, and adding more control objectives and so on. So who knows? Eventually, we could see this happening. Also, now we have other applications for batteries becoming more important, like these flying cars. Well, these electrical vertical takeoff and landing vehicles, and there could be opportunities also for balancing, active balancing and smart balancing over there, because this could also provide some level of fault tolerance operation, which is important if you are flying, right? But difficult to say. We have been talking about this for, I don't know, 15 years, and it's really not happening yet. Okay, you're welcome.
Thank you.
Okay, is there any other question? Yeah.
I liked your slide that you made yesterday. Thank you. So
Thank you.
One vote in positive, in favor. In the middle of that slide, you presented the state of the art in many aspects of battery management systems. And on the right-hand side, you showed what is mostly the future. My question, my curiosity is, where do you, so I think the right-hand side is where people are doing a lot of research right now and getting some early results. What is the biggest gap between the state of the art and, or where is the best gain available in your opinion? What is the easiest way to get a better battery management system?
Well, thank you very much. Well, in my view, there is an area that has not been investigated that much, and it is what is called derating. And basically, derating is about limiting current. And, well, we have seen some attempts. I have done that myself with, for example, model predictive controllers and things like this. But these kind of things are hard to implement. I think industry needs straightforward solutions that are relatively easy to implement, robust. And I think there is room over there for something that is in between complex optimization algorithms and heuristic-based. And I see that this could happen easily if we do a little bit more effort there, and we can include degradation-aware capabilities over there with not much effort. And this could actually improve a lot battery performance in many metrics. But if we are honest and we think, okay, how to really improve operation of a battery is all about the cells. I mean, we need better cells. Well, with the BMS, we are trying to cover up for that. But for sure, well, Professor, you know a lot about battery estimation, more than ever, more than anyone in this room, probably. And sure, state estimation is important, but I see also problematic to put into practice because of the computational power needed. And well, now I am working also in industry, and I see, well, how cost matters and how difficult it is to bring cost-effective solutions. And sometimes I also see that in academia we are putting a lot of effort on developing algorithms that apparently work very well, or they do work very well at cell level, but are very hard to bring to the pack level. Also, it doesn't make much sense to put a lot of effort on a model when you later have to operate with an aggregated model, because you cannot also bring this to the cell level when you go to the vehicle, because it would be just too expensive. But it's also true that with the cloud, with all this telemetry that we can do, help with artificial intelligence, this can also be one way to avoid this problem. So if we can send some key information, we can select well what is the information that we need to send, because of course there is capability, especially with 5G and 6G, which is coming to send all the data that you want to the cloud. But what do you do later with the data? It's also very expensive to analyze all this data. So also, I can see big room for improvement if we use the cloud in a clever way. And this is happening already. So also, a lot of these algorithms are difficult to implement on the edge, but perhaps on the cloud. But we need to select well what is the data that we are sending. It should be robust data, easy to analyze, and then that can be and everything should be automated. Also, I see a lot of opportunities regarding customization and personalization. Because, well, for example, if you want to predict lifetime or range, it's very important the person. What is the usage pattern of the vehicle, how this person is driving, what he's doing. And also with cloud computing and all the data that we can get from different systems integrating everything, I see also a lot of room to improve range estimation and also life estimation, taking that into account. But we can be speaking here all day. But this is perhaps what I see. Maybe you agree,
yeah,
maybe you disagree.
I have one more question, if I may. Is this I recently, some new BMS, like General Motors, are using wireless inside of the BMS to communicate from the sensors to the master. And I became aware that there is a research community that I did not know about that is looking at cybersecurity of battery management systems. Do you have anything to say about how industry is thinking about cybersecurity of BMS?
Yes. Well, cybersecurity is certainly a really big thing, and the best example I think is communication with the charger. So we see now new protocols, extension of the old protocols for communication that includes a lot of stuff related with cybersecurity. But this is not, so the standard is there, but the charging stations, most of them do not implement that. Also, there is a problem with compatibility with that because, well, it's not just, okay, I used to work with the old standard now, I work with the new standard. No, it doesn't work like this. So there is the main thing with cybersecurity, I would say that now is this connection with the charger and in systems that allow it connection with the cloud. Regarding wireless system, BMS with wireless systems, well, myself, I have experience with that. We are developing an IC in CTAC that is doing this wireless stuff. But to be honest, well, the thing is, in an electric vehicle, everything is so close to each other because this is part of the idea of optimizing the design of a battery pack in a vehicle. It should be very compact. Everything should be very close to each other. And it is even becoming closer because now we don't want modules anymore. Now cells will be integrated in a seamless way, forming one pack or even one thing with the chassis. So what is the point of wireless communication if the distance between cells is 1 millimeter? I don't see the point, to be honest. Maybe in other areas like battery energy storage systems or things like this, but also hard for me to see the true advantage of applying wireless communication within a battery system. But for sure, wireless communication is also being applied in chargers. You have communication through wires, but also in a wireless way. This is already there. The protocols are there. In the US also there is a big change right now. This is happening differently in different regions. Japan and China, they have teamed up, and now there is a new standard, Chaoji. In Europe, we have done that. And in the US, there is a huge partnership now between automakers to make the former Tesla standard for charging, the proprietary solution, Tesla solution for charging, a standardized thing, because it wasn't, although it was called North American Charging Standard, it was not a standard. You know about this better than I do, probably. So yes, it is happening.
Okay, is there any other question? Yeah, maybe.
Some online questions.
Yeah, wait a second.
Okay, maybe. Okay.
Okay, thank you. Am I on?
Yeah,
Okay,
your
thank you.
turn. Yeah.
Thank you. Great talk, Dr. Barras. I really enjoyed it. I also like this slide, and I had a question about sensors. You talked about the evolution of sensors from basic sensing through redundant sensors, which, as you explained, we're populating more sensors throughout the system. And then you moved into smart sensing, and I've had some thoughts on that myself, and I think you alluded to the fact that smart sensing now incorporates maybe some algorithmic integration of some of this sensor information. And I was wondering if you could elaborate on that a little bit, give some more examples, and perhaps give some thoughts on where you see that moving into the future, where we could make some gains in the smart sensing area.
Yes. Well, there is a big community, particularly in Europe, working on new sensing technologies. Also, if we're moving into physics-based models, we want to measure more things like gas, voltage, current, and surface temperature, right? So there are new ideas for fancy sensors that can go also inside the battery, inside the cell, not I would say, inside the cell. Of course, all the sensors are inside the pack or the module, and now it's about putting them inside the cell. This is a big challenge because, well, then you need to be in good alignment with cell manufacturer. They are not very happy about this in general. This also increases costs, can have safety and reliability issues. So it's a big thing. There are some ideas that can also work that are less invasive, I would say. So you don't need to put things inside the cell that probably have more potential. And this includes, for example, pressure sensors. So it's quite funny that actually pressure, we know that is such a big thing for battery lifetime, but nobody's doing research on that. And I think it's because of, in academia, we have all the people working in batteries, we have electrical background or electronics background, or of course the electrochemical background for the people who develops cells. And well, some people now also moving into physics-based models. Okay, fine. But most of the people working in engineering of batteries, our background is electrical and electronics, so we just skip the mechanical part. But actually, we know there are some preliminary studies that actually are telling us that pressure is a key factor for battery lifetime. It's like nobody wants to hear. It is. So we should sense that. Where should be the sensor? Inside the cell? Well, could be, and this could not be that invasive, I think. Could be outside the cell. We know that, for example, with prismatic cells and pouch cells, we have to pack them with certain level of pressure, otherwise battery lifetime goes down. But we also know that there are volume changes during charging, particularly with these new anodes that use silicon and graphite, because silicon expands more. But nobody cares about this so far. Well, when I say nobody, you know what I mean. But this is one thing. Also, there are people working in fancy ideas related with acoustic methods and infraacoustic stuff. This is also common methodology in mechanical engineering. Now this is also being incorporated. Now we see in cars also sensors for leakage of cooling cooling liquids. This is already there. I would say that I have seen this many times when we are opening battery packs. Also sensors for smoke, fumes. This is also a common thing. And it's also happening that we don't, in some cases, for example, in electric buses, and particularly in China, this has already been happening for years, that they have fire detection and suppression systems included in the vehicle. So why we cannot bring this to just light-duty electric vehicles if it is effective? So we can be speaking for hours. Thank you.
Okay. I think that we have another question from the chat.
Maybe we have time for an online question.
Yeah.
Fernando Caballero from CAF P&A asks, in which level of power do you recommend active balancing? Return of energy to module or to pack?
Can you repeat the last bit of the question?
He asks if you rather recommend, I think, return of energy to module or to pack.
Okay. Well, I cannot answer this question. What is clear is that you need bidirectional. If you want to get the most from an active balancing, you need a current level that is maybe around 0.2, 0.25 C, based on preliminary studies. And you need bidirectional capability. If you do that, moving energy from one cell to the next cell, or cell to module, or module to cell, is not that very important. It will influence in energetic terms and with respect to the achievement of the goal, of the control goal. Of course, it has influence in relation with how do you implement the power electronics and the overall efficiency of the system. And also there are some things related with, okay, can I connect a 4-volt cell with a 400-volt system? Well, you can, but it's not a very good idea in power electronics. So this is why we prefer to do cell-to-module and things like this. But for basic active balancing, this is basically done for low currents, and if what you want to achieve is just to be able to charge faster, you don't need anything fancy. If you want just to do state of charge balancing quickly, you can just use switch capacitor or inductor systems. So basically, you have some switches that with very high frequency are opening and closing, and then you have an energy storage element, which can be just inductor or capacitor, storing little amounts of energy, but quickly charging and discharging, and you can use this to move energy around. This is effective, it's the cheapest way to do it. Doesn't have many reliability issues. The other thing is much more complicated, and still we are not there.
Okay. Thank you, Jorge. I have one last question.
Okay.
According to a user's point of view, what do you think that is the big challenge in order to convince people of buying electric vehicles, apart from the price, of course?
This is the thing. Well, in Spain, we have a problem because we are losing purchase capability. So, I mean, we are not getting richer in a short way. So this transcends the electric vehicle area. And one way to get electric vehicles cheaper is to allow the Chinese manufacturers to sell in Europe. But from last week, we know that this is going to be a bit more difficult because, well, we have started some kind of, what can I call it in a in a polite way and in a politically correct way. But we have started some kind of battle with them. China is a great market also for European manufacturers. So is the solution to increase taxes for example, Chinese manufacturers? Well, I think what the European industry was asking for was more financial support, not taxes for the others. If we talk about, and if it is about making the decision about buying, we can see that in other markets, this is already happening. In Spain, we have a market share below 15%, but in Portugal, they have something that is becoming closer to 40% already. What was the main difference between Portugal and Spain? Because it's not about how much money do the people have in their pockets. What is the main difference is they have a better charging infrastructure and they have a better framework for subsidies. So here in Spain, if you buy a car, basically you pay VAT, and then maybe after 2 years you receive your money back. But you have to include this in your income tax form. And then you have to ask for another subsidy to pay back some of these taxes that you have paid. So the whole process takes around 3 years. And it's quite a lot of money because it can be around 9,000 euros or so. In Portugal, it's much more straightforward. So yes, it is about money, but also it's about how do you apply subsidies if you apply. And also, well, markets, it's important that we see competition in markets. If we start controlling markets, that can be a big issue. And probably I would say that the route of helping financially the automakers makes more sense than starting a war with taxes.
And also, Jorge, do you think that the range of the car or the charging times have impact on that decision of buying an electric car, or
Well,
do you think that it's only the price of the car itself?
The average electric vehicle in Europe that is sold these days has a battery pack between 70 and 80 kilowatt hour. This is a very good range, sufficient for almost all activities. The problem we have is that we have a very, very bad charging infrastructure so far. Maybe here in the Basque Country is better, but overall in Spain and all the data is not good. So you need a good charging infrastructure. From a technical point of view, the vehicles can deliver already. And if you have some more money, you can do some more kilometers. Fast charging is a reality. Of course, it is true that from the point of view of the BMS and the battery itself, it would be nice if the battery doesn't degrade if you do fast charging very often. And particularly in some sectors like, well, taxi drivers, VTCs, or people that are driving for commercial purposes their car a lot, can be a problem, because if they do a lot of fast charging, it's a problem. But
Okay, Jorge, so thank you very much for your speech. And let's move on to the next one. Thank you.
thank you.
So for the next speech, here we have Dr. Gregory Plett from University of Colorado, Colorado Springs. And his speech is entitled An Engineering Approach to Physics-Based Methods for Battery Management Systems, and it's about the modeling part. Professor Plett received his master's and PhD degrees in electrical engineering from Stanford University in 1992 and 1998, respectively. He is professor of electrical and computer engineering at the University of Colorado, Colorado Springs. His research focuses on control systems theory as applied to the management of high-capacity battery systems, such as found in hybrid and electric vehicles. Current research efforts include physics-based reduced-order modeling for ideal lithium-ion dynamics, system identification for physics-based models, parameters using only current voltage input-output data, estimation of cell internal state and degradation state, state of charge, state of health, state of life estimation, power and energy prediction, and battery pack fast charging. So, Dr. Plett, please, the floor is yours.
Thank you. Good morning. It is a real honor and a pleasure to be here, so thank you for the invitation. It is my second time in the Basque Country of Spain, and it is a beautiful place you live. Had a fantastic opportunity to visit the Rioja country yesterday, so I will try to walk in a straight line. You know what I mean. My colleague Scott Trimboli and I work at the University of Colorado in Colorado Springs, and so on this slide in the top you see a picture of where we live. It's also very nice, so anytime you have an opportunity to visit, please let us know and we can show you the campus at least. The mountain in the background we call Pikes Peak. It is 14,000 feet, so I think that is like 4,000, almost 5,000 meters high, so it is a very interesting landmark and it's a beautiful place. My background is in electrical engineering, and I'm going to be talking to you today about aspects that relate to electrochemistry. So many of you also are engineers, and you are learning about battery modeling and battery management and chemistry. You know that it is a challenging obstacle to overcome to learn about electrochemistry, so I feel the same pain. I've been working with battery management systems since 2001, so a little more than 20 years. These are some pictures here of some things that we do. So on the bottom left, you see one of our former students working in our laboratory. So we have some equipment that we can take measurements from battery cells. In the middle, you see some of our former students. We had a reunion about 1 year ago, and many of our former students came, and that was a really wonderful opportunity. Meeker, are you there? I don't think you, yes? No. Oh, I'm sorry. It must have been before you. And then on the right-hand side, our research really focuses mostly on understanding individual battery cells. Sometimes we do modules, but we also have this off-road electric vehicle, and some of our undergraduate students get to work on this, so they get some practical experience with their hands, and it is a lot of fun to drive this around. So we have a small team, I think, about 8 researchers right now working on projects. Most of them are master's degree or PhD degree students, but we also have 1 or 2 undergraduate students working with us right now. We already had a fantastic introduction to battery management systems in general, so thank you very much. That makes my job a little bit easier, especially because it helps me give a context for the work that we do. And mostly we work with algorithms. And algorithms are computer methods to calculate some values or something like that. So we are especially interested in how do we estimate the state of charge of a battery cell? How do we estimate its state of health? How do we estimate how much power is available? So on the previous talk, it was state of available power. Here, we usually call it state of power, but other researchers call it state of function. So you will also see that SOF, and also how much energy is available. There are many ways of making these estimates. Some of them are data-driven, as was mentioned. Some of them are empirical. Some of them are more physics-based. But most methods somehow have a model of the battery cell. So a model is a set of equations that describes the operation of the battery cell. And here I will mention 2 types of models. My understanding, maybe I am wrong, but my understanding is that almost all battery management systems that are in vehicles today use some kind of empirical model, like an equivalent circuit model. And so this here, I have drawn an image of an example of a circuit model. There are different circuits that could be used. They're not all the same. But we know that a battery cell produces a voltage, so the circuit has a voltage source. We know that a battery cell has a voltage drop on discharge, and so we include a resistance. And we also know that there are some time constants associated with when we apply current or remove current, how the voltage responds, and so we have resistor capacitor networks also to describe those. And so these empirical models are very, very good at predicting voltage when the parameters, the components of the model have the right values. There are some disadvantages of the circuit model, though, which is the motivation of the topic of my presentation today. And one of the disadvantages is that there's really no physical basis. You open a battery cell and you do not find a resistor, right? You do not find a capacitor. So there's not a direct physical basis for this model. It's something that we observe. We put the cell under test, we collect data and say, that looks like it could be described very well if I use this electrical circuit. But the circuit is only an approximation to what the battery is actually doing. And so when I collect data to find the parameters of this circuit model, I am making a compromise. Because it's an approximation, the circuit is going to describe the data that I collect very well. But if there is some operating region that I am not collecting data from, the circuit model may not describe those data very well. So if I only collect data at one temperature, then the circuit will not work at other temperatures very well. Or at some state of charge range, if I only collect data in some state of charge range or some life of the battery, I really need to collect a lot of data to make this model work well. And so it seems very simple at first, but in practice, to make a model that works reliably over the life of the application requires thousands and thousands of hours of battery testing to get good parameter values. So we say that the model interpolates or explains the data, the type of data that it has seen before, but extrapolating to different situations is not always reliable. That is something that can be overcome. Certainly the automakers and other applications are doing that now. They have, just enormous buildings full of testing equipment that is every day, every night collecting data. And so this can be done, and it is done. But something that is a fundamental limitation of a circuit model is that it can predict only the input-output behavior of the battery cell. So if we say the input is current and then the output is voltage, it could be the other way, but usually we do current input and voltage output, sometimes temperature output also. So a circuit model can predict these things well, but it doesn't say anything about what is happening inside the battery cell. And so a physical model is something that attempts to use equations to describe the physical processes or chemical processes that are occurring inside the battery cell. And because of that, if the physics are accurate, and we trust the electrochemists and the physical chemists to tell us this, but if we understand the physics correctly, then we can collect data from a smaller operating range and reliably extrapolate those data to a wider range. We trust the physics. And it also allows us to predict what is happening inside of the cell. Why is that important? So this is the most important point of my talk, and it is not, I think, in words on my slide. Why do we care about what is happening inside the battery cell? It's because this is what tells us if the battery cell is aging too quickly. It tells us if the battery cell is going to encounter some kind of a critical event that will be a safety problem or will make the battery degrade more rapidly than it should. So if I can predict the electrochemical state of this cell, then I have a better opportunity to make the battery last longer and be more safe. Those are my motivations primarily. So we would like to use physics-based models inside of a battery management system, but as was already mentioned, there are some significant challenges. They're not small, they are significant challenges that need to be overcome before these can be adopted in an industrial type application, a real setting. So today I will talk about six obstacles. One of them is obstacle number one: do we trust the physics model? We have to a little bit as engineers. I'm an electrical engineer. I am not a chemist, but I have to read the literature and say, okay, someone who knows about physical chemistry has given me this model. We usually use the Doyle-Fuller-Newman, or DFN, also known as the pseudo two-dimensional or P2D model. We often use this model as our starting point, but is it accurate enough? Is it missing anything important? So we will talk about that. If we wish to use this Doyle-Fuller-Newman model as a basis for battery management systems, then we have to consider, is it possible to find the parameter values of that model? And it turns out that if you look at the equations, the answer is no. But then we have to do something about it, so I will talk about that. And then even after you make that correction, how is it possible to estimate the model parameter values for commercial cells? Not ones that we make ourselves where we might know the materials, but a commercial cell where we receive the battery from a manufacturer and we have no idea what is inside, or very little idea. Then, okay, I have a model. I believe this model is accurate and it works, but I need to be able to implement this model in a simulation type of a framework for use in a battery management system, and it's a very complex model to simulate, so how do we work with that? And then I mentioned that the main reason for using a physics-based model is to predict degradation and aging, but degradation is not well understood. And finally, something that's different from computational complexity is conceptual complexity. So computational complexity is how many floating point operations are required to implement, one prediction. Conceptual complexity is how many years of graduate school is required to understand these things. So it's a little different question. So I'm going to give an engineering approach to at least a perspective. How do I think about these things? And maybe it will help you to think about these things also. And then the second talk given by my colleague Scott Trimboli will talk about some of the battery management applications. So I'm looking more at modeling, and he's looking more at applications. So let's begin with what is a physics-based model. Some very, very impressive work is happening at this university, so maybe this is too basic a slide, but I will present it anyway just to give the context of what is a physics-based model. So a battery cell has a negative electrode, it has a positive electrode. Lithium moves from inside of the particle of the negative electrode into the electrolyte, across the cell, into the positive electrode when I am discharging the battery cell. So I have lithium moving from one electrode to the other electrode. It's moving out of particles, through electrolyte, into particles. There's a lot of movement going on, and the state variables that we can use to describe this are listed here. So one of them is the electrical potential in the solid material, the electrode materials themselves. One is the potential in the electrolyte at any location in the cell. One is the concentration of lithium, or the amount of lithium maybe in the electrode materials. And so you can also see the X and T. X is location across the cell, T is time, and the concentration in the solid, we can assume perhaps that the particles are spherical. So there's a radial dimension to the concentration inside of the solid. And we're mostly interested in what's happening at the surface because that is the boundary between the solid and the electrolyte where the reaction happens. And then we care about the concentration of lithium in the electrolyte, and we care about the rate of lithium moving from the solid to the electrolyte. So those are the 5 variables of interest in the Doyle-Fuller-Newman model. And we can develop physical models at different scales. Some models are molecular scale, where they actually consider every single molecule in the substance, every atom in the substance. And you can imagine that simulating those models is incredibly complicated, and it's not necessary to do so, I think, for battery management systems, because we are concerned more with cell scale quantities than very, very microscopic quantities. The molecular scale will tell me what happens if I have a flaw in my material, but averaged out over a whole electrode, a single flaw in a single particle is maybe not too important. So we go from molecular scale to particle scale. Particle scale does particle at a time simulation. Continuum scale averages in some sense over that, and it considers the whole cell, but still maintains the X dimension and the R dimension and the T dimension. So smaller scales allow us to get more detailed, but they're slower to simulate. Larger scales average some of the smaller scale details away, but they still give us quite accurate simulations. So continuum scale models are what we see in the literature as being used for almost all attempts at battery management system models, starting there at least. So here is the set of equations that were defined by Doyle, Fuller, and Newman for the continuum scale cell models. And if you have training in electrical engineering, actually I began as a computer engineer. So I learned about programming languages and things like that, and I had never seen some of these symbols before, and it was very intimidating, very frightening to see these equations for the first time. And I remember when I was working on BMS algorithms using circuit models that I found some papers with physics-based models, and I said, oh, this looks important, and then I put it on my desk, and it was quickly, and it was not, that paper was not read for many years until I had to It's not so bad after a while. So we have the equations with these variables that I described on the previous slide. So the first equation, let me see, does this work? Ta-da. First equation describes the evolution of lithium capacity in the solid material. And if you maybe are a mechanical engineer, this would be more familiar, but this is a diffusion equation. It's the heat equation in spherical coordinates. So you realize that even though the equation might look frightening, it's a fairly simple concept that lithium just naturally moves from a high concentration to a low concentration location. It's just by random molecular movement. And say, oh, that's just a diffusion equation. And the next equation is the potential of lithium in the solid material, and that also is a diffusion equation of electrons. So instead of diffusion of lithium atoms, it's diffusion of electrons, essentially, so it's charge balance. The next equation is concentration of lithium in the electrolyte, and there are some constants there that might be unfamiliar, but overall, just in big picture terms, it's also diffusion of lithium through the electrolyte from a high concentration region to a low concentration region. And then we have the charge conservation in the electrolyte, which has two terms. One is the first term here is a diffusion term. The second term is a correction term based on the concentration of lithium in the electrolyte area. So those are partial differential equations. They're derivatives with respect to time, where, like there, for example, and derivatives with respect to space, like the divergence operation. And then the final equation is the coupling equation. This is what is known sometimes as the Butler-Volmer equation, and that says this is how quickly lithium leaves the particle and enters the electrolyte. So it's the reaction rate equation. So most of what we have going on is it's dominated by diffusion, and that's a simple enough concept, even though it's the equation looks very difficult. So this is the Doyle-Fuller-Newman model, and this is what we wish to solve. It's a little bit tricky to solve, but this is what we want to start with. Okay, so today there's 6 obstacles. Obstacle number 1, is this model good enough? And the model was, I think, first presented in about the 1990s. I want to say 1996. I might be wrong by 1 year. And it describes with those equations how a cell physically operates, but the last equation, that Butler-Volmer equation, assumed that there was one chemical reaction happening at the surface of the particle, and that was based on the open circuit potential of that particle. Accurate enough. Well, more recent research has said, there's a better way of describing this. This is the multi-site, multi-reaction model that was proposed by Mark Verbrugge and colleagues. And this says, okay, on the right here, I have this picture of the open circuit potential relationship of the NMC material, nickel manganese cobalt oxide material. And I can maybe write that as a table lookup, which is what the Doyle-Fuller-Newman model would do. But instead, these researchers have noticed that instead of writing it just as a table lookup with no structure, they can, they can use this structure here that says the electrode OCP is a summation of other simpler things, where each simpler thing is what we call a Nernst equation. It's a characteristic voltage, it has basically a local state of charge, and it has a shape factor. And over here, these colored dashed lines are the individual reactions that are happening that build up. If you add them sideways, horizontally, it builds up that overall open circuit potential relationship. And what is nice about the MSMR model is that it allows you to have different reaction rates for each one of these reactions. So you have a state of charge dependent reaction rate, and it also allows you to have different diffusion constants, rates of diffusion for each one of these, which allows you to have a state of charge dependent diffusivity, which makes your overall model much more accurate when you implement it with a commercial cell. So that was the first thing that we would recommend adding to the Doyle-Fuller-Newman model. That was not in the Doyle-Fuller-Newman model was a good description of high-frequency dynamics. The Doyle-Fuller-Newman model was designed originally for constant current events, and it describes frequencies of about 1 hertz and slower. So if you want to describe anything more quickly, that is happening more quickly, you need to consider something called a double layer, which is a capacitance that builds up naturally in the electrolyte near the surface of a particle. And when the particles have some charge on the surface, then the electrolyte is going to develop the opposite charge nearby, and then there's going to be another layer of the opposite charge and so forth. So this is well described as a double layer. In the picture, we have a particle with negative charges, and then the electrolyte nearby has positive charges. Maybe there's negative charges and then positive charges. That is the double layer. And you can develop equations that describe this, and this was done by Myers and colleagues, and we added just one component in our version of it. But the Myers equations can be written exactly as this equivalent circuit model, but this is not an equivalent circuit of a cell, and it's not even an equivalent circuit of an electrode. It's actually the equivalent circuit at one point between a particle and the electrolyte. So it happens everywhere through that. So I have a distributed equivalent circuit, and we've found that simplifying a little bit to this circuit at the bottom here actually gives us pretty good results. So what it adds in essence in this figure that was not in the Doyle-Fuller-Newman model is this resistor and capacitor here that describes the capacitance at the surface of the particle, and that allows much better description of higher frequencies. All right, so we've added two things. Another thing is that the Doyle-Fuller-Newman model assumes that all of the particles are the same size and that the distribution of particles are like tightly packed, and there's no description of how the distribution of particle sizes affects the operation and how the fact that the electrolyte has a very tortuous pathway. And so that can be well described in the frequency domain using something called a constant phase element, a CPE. I don't go into details here, but that can be added to the model. And then the final thing to add to the model is something which is a solid, an SOC dependence on the solid diffusivity. Diffusivity is a number that describes how easy is it for lithium to move inside the particle. So high diffusivity, easy to move, low diffusivity, difficult to move. And that is something that does depend on state of charge, and Baker-Verbrugge have a good physics-based model of that. So overall, that unformatted, oh well, close enough. For obstacle number one, the Doyle-Fuller-Newman model is a good starting point. It has some limitations, but somewhat recent research has overcome these limitations and has made continuum scale physics-based models that actually work very well. And so our recommendation would be to, when you're starting your design process, to start with this augmented Doyle-Fuller-Newman model, especially for present-day chemistries. More advanced chemistries like lithium metal batteries require a different approach, and even some things like lithium iron phosphate have some challenges that might require adding some more features to this model, but most present chemistries can be defined very well this way. Okay. So that is obstacle number one. Obstacle number two says, great, I am going to use this new model and I'm going to apply it to my battery cell, and I want to find the parameters of this model so that I can describe my own battery cell. Is it possible to do so? Especially, is it possible to do so without teardown, so non-destructively? So we encounter this issue of identifiability. So a non-identifiable system has at least two distinct sets of parameters that describe exactly, identically, the same input-output relationship. And it turns out that the DFN model is non-identifiable in this way. So we have to reformulate the model to make it work. So here's an example. That's an abstract idea, but let's consider something a little bit simpler that is not a battery example. So Newton, second law of motion, says that if I apply a force on an object, then that force is proportional to the acceleration that that object will experience. And so I can write it as force equals density times volume times acceleration. That is one way of writing Newton's law. So here's an example. I'm pushing on this object, and I measure force to be 1 Newton and acceleration to be 1 meter per second squared. and we want to know what are the density and what is the volume of the object using this measurement. I would ask for volunteers to answer that, but I won't. The answer is we can't tell. So if I have F equals 1, A equals 1, I could have rho equals 1 and V equals 1, that works, or I could have rho equals 2 and V equals 1/2, that works. There's an infinite number of combinations that would work, and so I cannot, even if I collect more data, so okay, that's one experiment, I do a second experiment, F equals 2, A equals 2, there's no new information there. There's not enough information for me to be able to determine the density and the volume without ambiguity. So Newton was smart. He didn't write it that way. Newton said force equals mass times acceleration. And so Newton took the density and the volume and lumped them together into this new thing called mass. And now I can say if force equals 1 and acceleration equals 1, then mass can only be 1. There's only one option. So that has taken a non-identifiable system of equations, a single equation, and converted into an identifiable system of equations just by lumping together two things that were not identifiable by themselves. So technically, we have taken an intensive parameter and we have converted two of them into a single extensive parameter, and that has made this an identifiable system. So we need to do that to the Doyle-Fuller-Newman set of equations. We start with the equations of the DFN model, and we go through this process where we normalize the length dimensions, we lump together parameters like on the previous example, and we, in the process, usually have some intermediate variables that look very strange, and so we just rename things, and it comes out looking okay. So here's the final set of equations, and if you remember, just instant recall from the previous slide, they look very similar. I had a concentration equation, now I have a normalized concentration equation. The theta S is concentration divided by maximum possible concentration, so theta S is a concentration between 0 and 1, normalized. Theta E is the electrolyte concentration normalized, so it has a value of 1 in equilibrium, and it's bigger than 1 or less than 1 in dynamic situations. I had J before from the Butler-Volmer equation. Now it's called I, so I is measured in amperes, which is very convenient for electrical engineers. IF is the Faradaic, which is the standard reaction. DL here is the double layer capacitor equation, and then IF plus DL is the summation of Faradaic and the double layer capacitor. So these equations look essentially the same as before, but things are lumped together in a way that at least mathematically, in principle, it's possible to find all parameters now from input-output experiments. But practically, it may be impossible or difficult because of signal-to-noise ratio issues. I would still need perfect data to make this work. So the recommendation to overcome the second obstacle is to be aware of it. I see so many papers in the literature where people are making physics models and they take a battery cell and they do some experiments and they do some kind of a regression and they get values that make the model look like it works from a current to voltage perspective, but the physical parameter values make no sense. So you have to be aware of this to get to make it possible to get the correct parameter values. And it's just a little bit of math, no problem. So now obstacle number 3 is, at least it's technically possible, mathematically possible to find the parameter values of a cell. Can we do it? Is there a practical laboratory set of experiments that we can perform to do it? And so here it's the same set of equations, but up on the right I show a physical cell just to say, aha, we are going to attempt it. That is a cell I will present some results in a minute. That's a Panasonic cell from a Ford hybrid vehicle, plug-in hybrid vehicle, and it's a 25 amp hour cell. It's NMC graphite cell. So can we find the parameter values? In the literature, when people are building physics-based models, there are two distinct approaches that they take to do so. One of the approaches is what I'm going to call a tear-down approach, where they disassemble the cell inside of a glove box, usually in some inert environment, and they extract components of the cell, and they perform specialized experiments and measurements using specialized equipment, scanning electron microscopes, and all kinds of things that I don't understand. You have extensive capabilities of doing that here at Mondragon. You've very, very impressive work done by Professor Laura Oka and others to do that. And in our lab, we can't do that. We don't have those facilities. And so instead, we are attempting to see if it's possible to develop experiments that we can execute on an intact cell without teardown, and then somehow take the data from these experiments and regress it to the parameter values of the models. So it's a nonlinear optimization to fit the data to the model, and we prefer the non-teardown approach because we can do it. At least we have the equipment to do it. And also, if I do a teardown, just the act of tearing the cell, of opening the cell, can change some of the parameter values, and so there's always some amount of regression or optimization that is necessary in any case. So 2 approaches. We prefer the non-teardown. Is it possible to do? So first, in context, estimating the parameter values then becomes a nonlinear optimization problem. So here's a sample optimization problem. This is, again, Newton's law, force equals mass times acceleration. I collect some acceleration and force data. Those are the blue dots, if you see them. And so I have a model, force equals mass times acceleration. I have measurements of force and acceleration, and then I optimize m, the slope of that line, to fit the data as well as I can. So in our case, we are going to perform different experiments for our battery model. Maybe I have C rate, plus and minus, and cell resistance measured versus C rate. And again, I have a model that the resistance is a function of my parameters, my smiley parameters. And I have my measurements, I have my optimization. So it's the same kind of a process, but it's now a nonlinear process. And nonlinear optimizations have challenges. There's lots of parameter values. Nonlinear optimizations don't guarantee that you find the best solution and things like that. And we started out with the problem that the model was not identifiable, but we've already reformulated, so that first problem is overcome. But because there are so many parameter values on the order of 30, depending on how you write your model, a nonlinear optimization with 30 parameters is guaranteed to find the wrong solution. Maybe it's an okay solution, but it's wrong. So maybe if I can design some experiment that isolates some of the parameter values so that maybe I'm doing an experiment that these parameter values over here don't have any impact on the results, so I can ignore them and I can focus my optimization on some smaller set, that would give me a better chance of finding good parameter values. So we're going to use a variety of inputs. We're going to use sub-models that describe those experiments, and hopefully we get some better results. So here is a sequence that we presently recommend in our lab, where we start with open circuit potential test. This does require a teardown. To do this, I have to open the cell and isolate the electrodes, make a half cell of the electrodes, and then charge and discharge those half cells to get the open circuit potential. But everything else does not require a teardown. The open circuit voltage test is a charge and discharge of the full cell. The discharge test is a higher rate discharge that helps me to calibrate some of the variables that I can only find approximately from the open circuit voltage test. A pulse test is a very, very high frequency test that assumes that the concentrations are not changing because it's such a high frequency, and so it allows me to find the more direct resistance parameters. And the EIS test, electrochemical impedance spectroscopy, is a sine wave test that allows me to find the slower frequency parameter values. And finally, the pseudo-steady state test is, again, a constant current test that allows me to find the final parameter values that are missing. So overall, through a sequence of tests, we get some final values from those tests and some initial reference values that go into the next step of the process. And by the time we get to the end, at least in principle, we can find all of the parameter values that we need from the model. Here's an example of applying this to that cell that I showed you. Over here, we have the open circuit potential of the negative electrode that we found. Here's the positive electrode. There's the open circuit voltage. We compare them in order to find the operating windows within the two electrodes of this cell. The constant current discharge has allowed us to take the positive electrode open circuit potential and then move it from the dotted lines to the solid line, which is a calibration step. The pulse test gives us resistance as a function of current, and there is SOC dependence, which is quite obvious, and there is a small current dependence in this test that is helpful to isolate the nonlinear effects of the cell. And then here are some electrochemical impedance spectroscopy results at different states of charge. Just some illustrations of the kind of data we collect and the kind of regressions that we do. So our recommendation on finding the parameter values of the cell is a hybrid approach. If it's possible to tear down the cell, then yes, tear down the cell in order to be able to measure the open circuit potentials of the electrodes, and then run the tests on the electrodes to do that. And if it's not possible, sometimes the cell manufacturer will have a legal agreement that says, no, you are not permitted to open the cell. We have some other options that are available, but the results are not usually quite as good. And then you perform the remaining 5 tests on intact cells to find the parameter values of the cell. Fourth obstacle is the computational complexity of simulating the physics-based model. The Doyle-Fuller-Newman model is, in my opinion, too complex to simulate in real time in a practical battery management system. I say it's my opinion because there are some research teams who are doing it in real time on a microcontroller. So there is some difference of opinion there, but I think that there is a reasonable middle ground where we don't have to use the full complexity Doyle-Fuller-Newman model, and we can approximate it very well using less computation. And if we do so, there's at least 2 different approaches to doing so. One is what I'm calling the intuitive approach here, where we look at the equations of the model and say, what is the slowest thing to simulate? And I want to speed that up. The slowest thing to simulate is the solid diffusion, because it is happening in the x direction, but also in the r direction. And so if I can eliminate the x direction, that would be great. And so the single particle model does that. The single particle model takes the entire electrode and says, I am going to represent that with a single particle. Not saying there's only one, but one of them represents the entire thing. And the same over here with the positive electrode. And so by simulating one particle instead of the entire electrode, I have some computational advantages. Another different type of approach is a more mathematical approach where you take the high dimensional thing and you project it onto a lower dimensional space in order to get a model that is as accurate as possible in that lower dimensional space. And so those are what we call the realization algorithms, and one example is the hybrid realization algorithm, which is one that we like. Quickly expanding on the first one, on the single particle models, they take the solid diffusion equation and they approximate it in different ways depending on the researcher. Some of them use finite difference methods, some finite volume, some polynomial approximation, some use POD-A method, and then there's other methods. I think Dr. Eker is going to talk about this later probably, including orthogonal collocation, etc. So lots of different ways of doing the simulation of the particle, and then many single particle models add a description of the electrolyte. They're called enhanced single particle models or single particle model with electrolyte or other things, and they also somehow approximate what's happening in the electrolyte of the cell using, for example, any of these methods. And then we compute voltage on using the solid concentration at the surface and electrolyte concentration at the edges of the cell and cell resistances. So that is a good approach. That's one approach. The other approach is the projection method. And the projection method at least has a possible benefit in that it can tell you not what's happening on average in the electrode, but what's happening at different spatial locations in the electrode also, which could be useful. So it gives you the x variable back. And then we can we can simulate all of the variables of the model, and then we can use them in our controls later on. The final model in the case of the realization algorithms is a state space model, which has new state equals a matrix times a previous state plus 1 times the input, and then some outputs as a matrix times a state plus a matrix times the input. So it's a diagonal state space model, which is computationally quite light to implement. The reduced order model generation, the projection is a little bit more complicated to do. We do it one time offline. We take the partial differential equations, we linearize them, they make transfer functions in the frequency domain. We combine them with the physical parameters that we found from our tests. We execute this projection method and we get the state space model that we can then simulate. So very different approaches. Actually, both can work quite well. We applied here the projection type method. So we augmented the Doyle-Fuller-Newman equations with the MSMR, multi-site, multi-reaction OCP method with the double layer, the constant phase elements, the state of charge dependent solid diffusivity. We reformulated the model, we did the lab tests, we found the parameters of the cell, and we generated a reduced order model using the hybrid realization algorithm. And here we have some results for a dynamic test and the error thereof. And this was maybe the first time we had gone through this entire process ourselves. There's a lot that could be improved, a lot still that we need to learn, but we are very pleased with the result. This was a 15th order model, and I'm thinking we can get that down quite a bit if we try hard. And the error compared to a physical cell, which was a different cell from the one we identified, so there's cell-to-cell variability, was about 23 millivolts, which again, I think we can do better ultimately, but that was a good first result. So, which reduced order model do you use? Is it a single particle? Is it a projection? It depends on what you need. If you need to have the parameter values available to you in analytic sense, in closed form sense, then a single particle model is probably the best approach. If you want to have the fastest computation, in my opinion, the realization algorithm is going to be a better approach. But again, these are maybe opinions at this point, and there's room for improvement. Okay, 2 more quickly. One of them is the whole point of a physics-based model is I want to reduce degradation and control degradation if at all possible. So great, so I have the model of a fresh cell, an ideal cell, but what happens when the cell ages? I need to understand that also if I want to prevent aging or slow down aging. And this wonderful picture that you're going to see your entire life by Burkle from Dave Howey's group in Oxford tries to show the complexity of the problem by all the possible degradation mechanisms that are known to exist, and there's, I don't know, a couple dozen of them. And the physics-based models are attempting to optimize a trade-off between life and performance, and so I need to at least understand something about degradation mechanisms, but really I need to understand the most important ones. I don't maybe need to understand all of them today. Which are the most significant causes of degradation or safety concerns? If I can model those, then that would be good. Okay, so we don't know a lot about all of them, but we know quite a bit about some of them. This is also from David Howey's group, excellent research team at Oxford, where they have made a paper that says these are some degradation mechanisms that have well-known models that are quite good. So we have pore clogging, we have solid electrolyte interface layer growth, we have got particle cracking, we've got lithium plating, things like that. So even though there's many, many mechanisms and many of them are not understood very well, the most important ones probably are understood well enough. And there's a paper by O'Kane, which is out of Imperial College, also an excellent group, where he is the first that I'm aware of that has combined, I think, 4 of these, maybe 5 of these degradation mechanisms in an interacting simulation and has done a very good job in doing so. And that's part of the PyBAM simulator, if anyone knows about that. So our recommendation at the moment is to look at this O'Kane paper for your application and then see if that is something that you can apply to what you are doing. Okay, the final thing is a shameless advertisement. So you can close your eyes if you want. It's like the final problem is these things are hard to understand. Yes, they are. But that's different from computational complexity, right? I find a lot of papers in the literature that say, oh, we don't like this way of doing state of charge estimation because it's so complicated. And most of the time, if you read it carefully, what they mean is we don't understand it. It's not computation, like a Kalman filter, for example, is computationally pretty light, but conceptually difficult the first time you build one. So conceptual complexity is how hard is it for me to learn this and to understand it. And the only way that we know to overcome this obstacle is to spend the time to learn it. But there's a lot of materials available that can help you with that. At the beginning there were not, and there are more available now than ever before. So there are some textbooks, I'm showing ours just because I know them. So those are available. We actually have some classes that are online at our university, and so you can download all of the lecture videos for the Blue Book, and you can use those to help you study, for example. The third book, the red one there, is quite new this year. It has a table of contents that describes all of these things. It talks about how do I eliminate the redundant parameters to make the model identifiable, how do we model impedance of this cell, how do we estimate parameters, how do we do time domain simulations efficiently. This is what I'm talking about today. How do we estimate cell internal variables, how do I think about degradation, and how do I control the cell to do fast charge and power limits, and my colleague Scott Trimboli will talk about many of those topics today. The field is advancing in maturity, and there's more and more resources available to help you learn the materials, and hopefully you can find some resource, a book or a course or something that is the way you think and is helpful. There are some legacy methods on equivalent circuit models that are available in this book. Our recommendation is there's no shortcut, and we just recommend some study, getting a good friend who understands this, and your friend can explain it to you. That's maybe the best way of doing it. But there are resources available to help. So to close, I know that I am the only thing standing between us and our coffee in a couple of minutes. I'm a little late, sorry. We can develop battery management system algorithms using empirical models or physics-based models. The empirical models are limited because they cannot predict what is happening inside the cell, and the physics models are beneficial because they give us insight that allows us to compute estimates of these things and hopefully can be useful to make the battery management system more safe and make the battery pack last a long time. We talked a lot about some obstacles that people have identified and also some engineering concepts, some perspectives on how to overcome these obstacles. And the next talk is going to talk about how to then use these models in algorithms. So with that, I will conclude and take some questions.
Thank you very much, Professor Plett. So, as you mentioned, if you are interested in going deep in this field, you can check the book. Or instead, if you have any question here, you can ask directly to Dr. Plett.
Yeah, thank you for this very nice presentations. I really enjoyed it. And I'm very glad that you, as a electrical engineer, managed to learn the chemistry. That means that there's hope for the rest of us also. My question actually goes for your slide 8, where you touched it briefly. So if I understood it correct, that for those new types of batteries, technologies, which will come in the future, I know there are some companies working replacing graphite with silicon, and we have some metal batteries and solid-state batteries and so on. Does that mean that all the physics-based modeling basically remains? It's just the parameters which changes. So you only need to do maybe some slightly modifications for that to work also on new technologies.
Yeah. No, that is an important question. And unfortunately, engineering is always behind science. So the science happens first, and then the engineering happens. So the science is coming up with new technologies of new chemistries, and then the engineering has to see, does the same method still work with the science? And sometimes yes, and sometimes no. So you give some examples. So one of them would be solid state, and if it's a lithium-ion battery with a solid state, then my understanding is that everything should still work with different parameters. So in fact, the Doyle-Fuller-Newman first paper used a solid electrolyte in their paper. But if you're talking about a lithium metal negative electrode, a lithium metal anode, instead of a lithium ion type anode, a particle anode, then the way that the negative electrode works is fundamentally different. So instead of using exactly the same equations, you have to use the same ideas. So you have to start over a little bit. And so we've done some work in our team. I can share some publications with you during the break if you would like, where we have done some work with lithium metal battery systems, and in some ways they're easier, in some ways they are more difficult. For example, in lithium ion, you have to be careful when you're charging because you want to avoid lithium plating. With lithium metal, you have to have lithium plating, and so it's a different way of thinking. Sodium ion we have not worked with. Our understanding is that they are very similar. My belief, without specific knowledge, is that yes, you can use the same equations with different parameters, but I don't know that. Silicon. Silicon has an enormous amount of hysteresis to it, meaning if I charge to a specific state of charge or if I discharge to a specific state of charge, the rest voltage will be different. And if we don't model that hysteresis carefully, then we will have a lot of uncertainty in our state of charge estimates. And the same is true with lithium iron phosphate. There's a lot of hysteresis in the material. There are some empirical models of hysteresis. We've published one, and so Baker, Verbrugge, and Shao have published one that work okay. But they don't describe the physics directly. And so there's some recent work. There's another paper I can share with you. One of our colleagues, where is he? Germany. You remember what university? Beirut University, where they've done a semi-physical model of hysteresis that matches at least the idea of the physics, and it looks like a fantastic approach to us, but it's brand new, we haven't tried it yet. So that would be one way, and in fact they have an equivalent circuit model that does it really well. So there's still work to do, I think, with iron phosphate. Iron phosphate is an incredibly important chemistry, as many of you might be aware, because it's very inexpensive, it lasts forever, but its voltage curve is almost completely flat, so if I measure a voltage, I have no idea what is the state of charge. And especially the hysteresis then changes the voltage curve depending if I'm charging or discharging. So if people can advance our understanding of iron phosphate, that would have an industrial application, which would be very important. What else did I say here? So we did sodium ion. Lithium sulfur is another one that I don't have here, which is completely different. And if you do a discharge curve of lithium sulfur, it starts up here and it goes down here, and then it goes back up here, and then it goes down here. So it's not monotonic. It doesn't continuously go down. And so we have not worked with that. Some colleague of ours has worked at it at the University of Maryland, and he has some preliminary results. But it looks like that is going to be very, very difficult to do battery management for. And the physics models that we have today don't describe that exactly, because that is a chemical battery. It's not an insertion battery, if that means something to you. So in some ways, yes, we can use the existing models. In some ways, no, that they still need to be developed.
Thank you.
Yeah, we have another question. Okay, first, Edu right here.
Thank you very much. So first of all, thanks for the presentation. I enjoyed it very much. I just wanted to ask you a couple of questions about the parameter identification method that you briefly presented. So this kind of method, it's like, or seem to be like really appealing for more industry or closer industry applications, since it's based mainly in voltage current measurements. So first question is, even if those measurements are simpler, is the voltage accuracy, typical voltage current accuracy that we have in a lab enough for implementing those methods, or do you need any specific sensors, a specific signal treatment, or any kind of method? And the second question would be if that method that seems close enough, do you have any insight on the internal variable estimation integrity or accuracy after applying it?
Okay. So the first question was, I have a lab with equipment, is it good enough? Yes. I don't know. So for the open circuit potential testing and open circuit voltage testing, what we are doing is we are doing a very slow discharge and a charge of either the electrode or the full cell. And we started with doing this at a C over 30, C divided by 30 rate, and that is okay, but more recently we have been doing it even more slowly to get higher quality data that has less polarization. So C divided by 50 or C divided by 100 even to do that. Is the equipment capable of controlling current accurately for a long period of time? That is a question. The voltage sensor accuracy is less important because that averages out, but again, of course, you want good voltage. In our open circuit potential testing, we have a Gamma, which is designed really for electrochemical impedance spectroscopy, but it has really good voltage measurements. We use that, it seems okay. For the open circuit voltage, we have Arbin, it seems okay for that. The discharge test is a faster constant current, as is the last test. We use an Arbin, it seems okay. There doesn't seem to be a problem there. The EIS test is a standard electrochemical impedance spectroscopy. You can buy an instrument that is specialized for that, like Gamma or other companies. We don't have any problem with that. For a very large cell, you have to use a fairly large current, even to get like C over 50. So maybe the equipment we have is not great for a 200 amp hour cell, but for a medium-sized cell, it's okay. The pulse test is the one that is the biggest mystery, and that is where we take a resting cell and we apply a very short duration current pulse to it, but very high magnitude. And we had some very good results, I think, with the Panasonic cell we took 3 Gammas and we put them in parallel to get 100 amperes of pulse. But that is not what the equipment is designed to do, and so it does it with some kind of imperfect quality, but we still got some good results. Then we tried it on some other cells and we got some bad results. So the pulse test is the one that we don't know right now. Is this going to give us good results in general, or what is required? But I saw a paper recently, and maybe I can give a reference if anyone sends me email, where someone was doing lightning testing on battery cells. So they were doing surge protection testing, and there is some equipment that you can purchase that is designed to simulate lightning. And it goes 0 amps and then big current and then goes down in maybe 60 microseconds. And they applied it to a battery cell, and the curves that they showed in the paper were exactly what we expect the resistance to look like as a function of different current. So maybe if we could buy that equipment because it's designed to do high current pulses, that would be a good approach. So I don't know. The equipment is not cheap. I said, oh, let's go buy one, and then I got a quotation. It was maybe 50,000 euros. Just to see if this works, that's a lot of money to invest. So I don't know. So that was one question that you had. Is the standard accuracy of laboratory equipment good enough? I would say yes, except maybe the pulse test. The second question was, okay, I make this model and then I want to estimate the electrochemical states with this model. Am I estimating the correct thing? In simulation, yes. In practice, we don't know. Because in practice, you would have to somehow insert a sensor to validate inside of the cell. And maybe you can do that with a small prototype cell with a reference electrode, for example. We have not done that. I think some other people have done that, and they got some good results for what they tested. There's so many research questions. So if any of you are looking for a PhD topic, talk to Dr. Edu here. He will help you. That's the best answer I have right now.
Okay, thanks a lot.
Okay, here we have a couple more questions.
Hi, Professor. My question is, when you augment the DFN by considering, for example, this MSMR, the CPE elements, and etc., does that affect the identifiability somehow of the parameters?
It can, and so we have taken that into consideration when we have lumped together the parameters in what we call a lumped parameter model, yes. Just so mathematically, the idea of identifiability is if I collect an infinite number of measurements, is it theoretically possible to find the parameter values? So yes, it is identifiable when we do this. Practically, we have to also consider the sensitivity of a voltage measurement to a change in a parameter value. And some of the parameter values are very, very difficult to see in a voltage measurement. For example, usually the electrolyte conductivities and things related to that. So it still may be very difficult to get a good value of the parameter, and that goes back to Dr. Edju's question, when I simulate the model, does it mean anything? And I think that is a somewhat open question, but our belief is that we can see the things that are most important to voltage, and we hope that those are also most important to degradation.
Okay, and the last one.
Hello, thank you for a great presentation. I have some questions about this estimation of model parameters, because basically what you have presented in this slide is of offline estimation. But then there is the problem of online estimation, but you cannot at that time do this cleverly designed lab tests. You just have the data that you have.
Yes.
Unless you add something else that there is not right now in the batteries, like an EIS system or whatever. And then there is another assumption, and it is that the cell temperature is constant, and we know that we are particularly very interested in fast charging, and with fast charging usually there is a lot of cooling going on, and cell temperature can be non-uniform, and there is a trend right now with larger cells and so on. So I see these two as big obstacles as well. What do you think?
Yeah, so the question, if I understand correctly, is maybe we can estimate parameters and model a cell in a laboratory controlled situation, but in a realistic situation where I've got temperature gradients and I cannot control the current, what do we do then? That's a very relevant question, and I agree that this is a challenge. So one way of thinking about it is I need to understand how to do this in a laboratory first, because if it is impossible to do it in the laboratory, then it's going to be impossible to do it in an application. So if it is possible to do it in a laboratory, then maybe I can refine the method to be able to somehow adapt it, adjust the method to do it in an application. Another thing to consider is in the laboratory, it's possible, if you have the right equipment, to do the teardown parameter estimation where you can open the cell. But inside of your electric vehicle, while you are driving down the road, you cannot do a teardown. It's not recommended. So having this more mathematical approach, at least if I require a teardown to find the parameters that change over time. This can give me a fresh cell model, but if I have to adjust the parameters as they change versus time, and if I require a teardown to do it, then this is not going to be a practical solution. So being able to do the optimization on fresh cell data gives us at least some hope that we can find a way to do it in real time or in situ or cloud or something in an application. But we don't have a final answer for that yet. We have some ideas. I think Dr. Eker is going to present probably, are you doing the SOH? So he has some method that works very well for estimating some of the parameters in real time that he will present later this afternoon. I'm very, very pleased with the results that he's getting in that work. And then there's a few methods to do it, but it's a very, very young research field. So again, any PhD students looking for a research topic, you can talk to Dr. Unai or Dr. Edju or Dr. Eker maybe now. I don't know. Yeah, that's a fantastic question. So I gave you 6 obstacles to commercial adoption that I had some answer for, and I didn't give you the other questions I don't have answers for.
Okay, okay, Professor Plett, thank you very much.
Thank you.
For your presentation and for the answers. And now we are going to take a break just to stretch our legs. But first, we want to take a picture outside near the building, just as a reminder of the meeting. We will see if it rains or not. If it's raining, we will try again later, okay? Hello again. Now we will continue with Professor Trimboli, and he is going to talk us about an engineering approach to physics-based methods for battery management systems, but more focused on the control part. He is an expert on model predictive control, and Professor Trimboli received his bachelor's degree in engineering science as a distinguished graduate in 1980 from the US Air Force Academy in Colorado. He received his master's degree in mechanical engineering with a Guggenheim Fellowship in 1981 from Columbia University, New York, and the PhD degree in control engineering in 1989 from University of Oxford, UK. Professor Trimboli's research focuses on the development of control strategies for the management of high-capacity batteries, and such as the use on electric vehicles. He is currently University of Colorado, Colorado Springs principal investigator for the Multi-University National Science Foundation Engineering Research Center for Advancing Sustainability through Power Infrastructure for Roadway Electrification, where he leads a team building a state-of-the-art software toolbox of battery modeling and control utilities. Other research efforts include physics-based modeling of lithium metal batteries, reduced order modeling of lithium-ion batteries, physics-based modeling of lithium-ion degradation dynamics, as well as predictive methods, as I said, for power estimation. So please, Professor Trimboli, the floor is yours.
Thank you, Eric. Let's see, there's my first slide. Thank you so much. It is indeed a privilege to be here back in the Basque Country. Love traveling here, love visiting here, love meeting the people here. It's a real honor and pleasure. Okay, as mentioned, I'm going to give you a talk that keys off of many of the main points made not only in my colleague's previous talk, but the talk before that by Dr. Barreras that really, I thought, gave a nice comprehensive framework for the battery management system. And we're going to dive a little bit deeper into the ideas associated with algorithms. My colleague talked about the models. I'm going to kind of migrate that idea into its implementation with respect to the algorithms. And by way of a little background about me, as mentioned, none of us really have come into this topic as battery people from the beginning, right? We came into batteries from something else. My original education was in engineering mechanics, so I was kind of a mech guy way back when, and then I worked my way into control theory and double E. And of course, when you're a control guy, you know, controls is a pretty wide-ranging field that is tailored to an application, right? It really doesn't make sense unless you have an application. And for many years, my application was aerospace. I worked in the aerospace industry, satellites, space structures, and things of that nature. And then about 2009, 2008, I met up with my colleague, Professor Plett, and started to learn about batteries. Before that date, probably only knew how to maybe spell a battery or put one in a device, but since then have learned a lot. We consider ourselves the term I use is a backdoor electrochemist. Came into electrochemistry right through the back door, not the front door. And so I'm not an electrochemist, but we, as controls engineers, need to understand our application space in order to be effective. And so you really, really have to learn your system in order to be a good controls engineer. All right, so what am I going to talk about today? We've already heard about the role of a battery management system, and so we're going to use that idea in order to achieve the safe and reliable and effective use of a lithium-ion battery in a system during operation. And we can boil down the requirements of a good BMS to an accurate battery model as presented by my colleague, and then well-designed algorithms that exploit the information inherent to those models in order to achieve a desired objective. There's an entire taxonomy of battery models that we can employ. Let's turn on my clock here to make sure I don't go over time for you here. Whoops, maybe it won't. Oh, there we go. All right. And I give an example taxonomy over there on the right-hand side. And at the highest level, we can boil these down to the empirical models. The equivalent circuit model is certainly one of those, and then sort of a family of the physics-based models about which you have already heard. And we could probably add to that taxonomy, as Dr. Barreras pointed out, the data-driven, the purely data-driven models. And then there are, of course, sort of blends between these different model forms. From a controls perspective, we view that the best models capture truly the underlying behaviors, right? And I call this an information-rich model. Because again, coming from the aspect of a controls engineer, I want to accomplish an objective. And in order to do that, I need information around which to build my control system, so I look for an information-rich model. We know from the previous presentation that electrochemically based models are perhaps ideally information-rich, but on the other side of that coin, they are inherently complex. And you saw a discussion, or you heard a discussion about not only computational complexity, but conceptual complexity as well. Therefore, we're on the search for a simpler form of model that is information-rich, but also simple enough for implementation. Now, I mentioned that I'm an engineer, and an important distinction to make, perhaps, before I go further, is the fact that, a lot of what we do is mathematical, but I am not a theoretical mathematician. I'm an engineer, and there's a fairly distinct difference. And many of us have perhaps encountered the experience, I know I have, where I see a wonderful technique emerge from the control systems literature in academia. Boy, that's a beautiful thing. It achieves, performance to the nth decimal point, but then try to implement that, right? There's usually a very wide disconnect between what the theoretical mathematician can produce and what the engineer can employ. And so I'm going to go through this with sort of an engineering mindset. And my own engineering mindset is based on the predicate that I want to do as much as I can with as little as possible, right? I want simple things that give me good performance. Doesn't have to be perfect, right? It doesn't have to be to the nth degree, but it certainly has to be good enough. And in many regards, we have to take a little bit of care in how we define good enough. But I want you to understand sort of that background theme. My colleague, Professor Plett, presented 6 key obstacles to using physics-based models. I'm going to talk about the algorithms that utilize those models and talk about that in the context of several topics. Again, you've seen this, but you've seen this idea, but we've had coffee since then, so you may have forgotten. I'll remind you. Physics-based models and this is sort of our premise, right? They enable the possibility of advanced control actions based on the internal electrochemical measures, right? But they're generally deemed as too complex for embedded real-time architectures. So next generation battery systems are instead going to have to, rely on these reduced order forms for practical implementation. And I guess I realized that was important enough, I put it in there twice. So several techniques have emerged in recent years, right? The most promising, in our view, are those that have the smallest model package. In other words, the smallest model order requiring the least computation, but still embody the richness of the information set. Professor Plett kind of divided these into 2 groups, and we work in the same research group. I had the same 2 breakdowns. The subspace-based projection methods, and these are 2 used in our research group, and the single particle model. And the fundamental difference between these 2, as pointed out before, and I'll highlight this in a little more detail, are that the subspace-based projection model, to take a full order complex version down to a simplified version, is that it's mostly numeric. I'm going to use some numeric mathematical techniques in order to derive this simplified model that somehow, almost magically, retains the electrochemical information. The single particle model does something quite different. It starts from a different basis. It says, I'm going to take this full order model, I'm going to examine the physics, the physical equations, and I'm going to see if I can sort of simplify the equations themselves. They still retain their physics-based significance, but now they're perhaps a little bit less accurate, but they still have meaning. Right, so the reduced order models. I'm going to focus on what we call this XRA version of our subspace projection method and go into a little bit of detail. I know you've seen that picture before. I'm going to kind of go through that in a few more steps. Let me talk about this XRA. The RA part of that stands for realization algorithm. And what it means is it's a numerical method where I've taken a bunch of input-output data from my system. And this could be rendered either in the time domain or equivalently in the frequency domain. And I have sets of data. And now I'm going to tease out of that data the underlying sort of dynamic modes of operation. And that particular technique comes under the heading of realization algorithm. We have a few different flavors of that, hence the X in front of it. I think we talked about some of those earlier, the DRA, CRA, right, discrete time realization, continuous time realization, and then the hybrid realization, or HRA, that Professor Plett talked about moments ago. All of these bring us to the same place, but they have different numerical attributes, different advantages and disadvantages that I won't dwell on, but just to let you know that there are different ways of doing this. The physics-based ROM, that's what I mean by this PB-ROM here, reduced order model, has typically a single input, and that would be the current. That's the control input that I can really use to modulate the activity of my underlying system, although in some cases I can perhaps use temperature, ambient temperature environment, if I can control that. That's another control input. Here I'll specify current. That can predict, from an electrochemical standpoint, a myriad of these underlying electrochemical variables. Now, I'm leveraging the work of the previous presentation. I'm not going to go through that model again. The DFN model is the one in which I'm basing this discussion, but I'll remind you that we have several elements of interest, parameters of interest here, that derive from the lumped form model. And a few of these are here. For example, the concentration of lithium at a particular point in one of or both electrodes, the concentration of lithium at the surface of an electrode particle, and the various potentials that exist within the various electrodes, as well as the I sub F. It's the lithium flux, right? It captures the rate of movement of lithium through the cell. All of these will play a role, or can play a role. Again, I'm a controls engineer zeroing in on what can I exploit here to do really good things for battery performance by way of a control system. So these can be further introduced, if I know what's going on in my ideal model, as inputs to a degradation process. And that's assuming I understand how I can model degradation. Some of that was alluded to earlier, and some I think will be presented by Iker in the later talk. And if I can do that, then I can start to envision these control strategies that can produce some accurate predictions of how my cell will behave for different situations. So let's just walk you through very quickly how this XRA works. It starts with that set of partial differential equations that you saw earlier, but those are nonlinear things, right? We're going to rely on transfer functions as an input to my XRA. Transfer functions are inherently linear, so I've got to linearize all this. So I'm going to linearize that model, and then I'm going to Laplace transform it into transfer functions. Well, the transfer functions themselves are interesting, but they must be populated with values that reflect the actual system, hence all of the system identification that you saw in the previous lecture. Once we perform all of those tests and we regress all of these variables, we populate the transfer functions, and then it goes to that middle green block, and that's where the magic happens. And I'm going to not cover that because that would be about a 2-hour lecture of how the XRA works, but it works by a technique we call subspace projection. My colleague showed a picture that tried to represent this, where I'm taking a multi-dimensional thing and I'm basically casting a shadow of that onto a smaller dimensional subspace. And I want that sort of shadow to incorporate the most relevant dynamic pieces of that behavior. And then I'll turn that into what we call a linear state space model, an example of which you also saw. So it's that linear state space model in discrete form that's going to form sort of the basis of what I'm going to incorporate into these control algorithms that I will talk about. And there's just one example of one of those rather nasty-looking transfer functions. It's linearized, but as you can see, it's not what you would normally expect, right? It's not an ordinary polynomial over a polynomial. But it still admits a frequency response, which is important for us. All right, moving on. Let's see. We talked about this, and this is kind of the baseline here. We see great benefits, and I think a lot of people see great benefits in the incorporation of physics-based models into algorithm development. But they've really been slow to gain any traction in industry, and there's a lot of reasons for this. One of the reasons is, and we work principally with the automotive industry, although not exclusively, is that many of these big industries are very risk averse, right? Very hard to take an existing thing that works okay and then move it to something else, even if it might work better. An example for this I've seen in the controls industry, and I studied controls decades ago. And back then, I remember when I was an undergraduate control student, they said, funny thing here in 1977, 90% of all the control systems implemented in industry are PID controllers. Okay. And I teach control systems today, right? I'll teach it in the fall. And I'm going to say to my students, funny thing today, 90% of all control systems implemented are PID controllers. Wow, we made a lot of headway, haven't we? Why is that? Well, there's lots of things that have come out, but right, there's a lot of resistance to changing something that works okay. Anyway, that's one of the reasons. There are several others that are more specific to this particular topic, and I'm going to kind of capture these in 4 topic areas that strangely appear in 2 different fonts. The first is state estimation of internal electrochemical variables. And that's different from what Professor Plett showed you earlier. He talked about identifying the parameters, right, using experiments and then assigning values to them that reflect how the battery behaves. State estimation, I'm going to talk about taking variables of interest that we wish to track and monitor in their time domain evolution. We want to, at any point in time, have an idea of where they are, of what their values are. So this is a dynamic estimation of state. Second one, and this was talked about by my colleague and will be talked about again by Eker, but that highlights how important this is, the representation of cell degradation mechanisms, right? The essential Doyle-Fuller-Newman model you've seen today is an ideal cell model. That's what a cell would behave like right out of the factory, right? Brand new, beginning of life. But these things change. You all see this every day with your consumer electronics devices. Gee, my phone used to hold charge for 8 hours. Now it's an hour and a half, and then it goes off the cliff, right? What's happening in there? Well, a lot of things are happening that degrade its performance in a lot of ways. And by understanding these degradation mechanisms better, it enables us to build controls that can mitigate some of these effects. And finally, the last 2 will be more application-oriented things I'd like to talk about. One is computation of fast charge profiles. All right, everyone's interested in fast charge. How can we do this safely and reliably? And the other is estimation of dynamic power limits. So these are perhaps 2 of the most important aspects of battery performance that the industry has certainly indicated to us a great interest in doing well. And so, once again, I'm going to take each topic and I'm going to develop it a little bit for you and then talk about some perspectives on overcoming these obstacles. And what you're going to find is that most of these perspectives are going to be sort of presented in the way of future directions. So those of you looking for future research topics, I'm going to add to that list here today. All right, let's talk about internal variable state estimation. As you know, all the critical BMS computations that we've been talking about rely on accurate description of what we call the state of a lithium-ion battery at any moment in time. Some examples of what I mean by a state. So a state is a snapshot or a picture of attributes of that cell that tell me something about how it's performing right now. And for an empirical model, for example, an equivalent circuit model, I may be able to track its terminal voltage, its surface temperature, and let's say its state of charge. And if I can take those three variables and stack them up into something we usually in mathematics package as a state vector, and then evolve that over time, I have some picture of how this battery is behaving. That's a rather simplified state vector. I can add to that if I now incorporate a physics-based model, where I can add such things as, lithium concentrations, because those might be important, right? If lithium concentration in a certain location of my electrode gets too low, I could start to destroy its structure, and bad things could happen. So it might be wise to track that. Electrode potentials play a role in lithium plating, we know, and so it might be nice to track those. So let's augment my state vector with some electrochemical quantities that would be useful for control. But here's the question, how do we get these values? Well, two ways, and they were illustrated, I think, earlier at Dr. Barreras' talk. We can either measure them, or we must estimate them, right, from quantities that we can measure. In practice, those of you familiar with this field know that most of the variables of interest, certainly the internal electrochemical ones, can't be measured, right? We don't have nifty little sensors that we can insert in the battery that says, the electrode concentration at the surface of the negative electrode is this, right? We don't have that sensor. So the best we can do is to deduce its value from algorithmic means, and that's what we'll talk about next. There are a number of ways to provide these estimates. And again, those of you familiar with estimation and control have heard of things like system observers. We take a modeled system, we propagate that, and we use that as a basis to figure out about what's happening inside the model. There are various flavors of these system observers, if you will. The one that we gravitate toward is, of course, the Kalman filter, which is a very specialized system observer that has some optimality properties associated with it. The basic idea of a Kalman filter is actually pretty simple. One of the key reasons we use a Kalman filter is, as mentioned, inside of a certain set of assumptions that have to do with the probabilistic descriptions of its uncertainty, a Kalman filter is optimal. It's an optimal estimate, right? Another advantage to a Kalman filter that we really like is that a Kalman filter, in addition to giving me a central estimate of what that parameter is right now, it can give me an idea of how confident I am in that estimate. In other words, I can put confidence bounds around it. And that's really nice, and it actually talks to this idea of derating, and that's how I think of it, that was mentioned earlier, because I'm interested in safety and reliability, so I'd like to put some conservatism around this. So I'd like to back off, the hard estimate, that central estimate, with a little bit of conservatism in order to ensure that I'm inside of a safety envelope. Another point to make, a standard Kalman filter, and I'll talk about the algorithm here in a moment, although that's not very readable, is designed for linear systems, right? Linear systems. Well, the battery's not linear. Yikes, right? What are we going to do? So there are flavors of the Kalman filter that deal with nonlinear systems. There's a family of these. Two that we employ exclusively are known as the extended Kalman filter, sigma point Kalman filter. Okay, two different flavors. They both work with nonlinear systems. The basic difference is an extended Kalman filter utilizes the point-wise derivatives of the state equations of my model. Sigma point filter avoids the calculation of those derivatives, which, by the way, a lot of students enjoy the sigma point Kalman filter for that reason alone. They don't have to go and do all those derivations of those derivatives. Sigma point Kalman filter kind of scatters some points around the operating space, figures out the evolution of the state equations, and then deduces the essential nonlinear behavior from that. We're often asked, gee, which is better? Well, the answer is it depends, right? We have seen good performance from both. In some cases, the extended works better. Some, the sigma point works better. Depends on where you are in the operating space. So it's it tends to be very problem dependent. So in this particular case, we can predict the state, the full state vector if we engineer our Kalman filter properly, and use those in control algorithms. I know that's hard to read on the right, but basically what it's showing you in the blue box is there we have 2 steps in the Kalman filter process. The one is prediction. I'm going to use the model, put in my current input, and I'm going to jump the model ahead 1 step and say, where am I 1 second from now? And then in the second block, in the green things that you can read, it says, I'm going to take a snapshot measurement of where we actually are, compare that to where you predicted I'm going to be, and I'm going to use the difference between those to generate something called a Kalman gain, and then modify that predicted value in order to make it more precise. Okay, so 2 steps, prediction and correction is essentially what's going on. Here's a very easy example of a state of charge estimate. Kalman filter estimate is going right down the middle. We have a truth. How can we have truth of state of charge? Well, we really can't, but we can derive it from very, very complex, right, full order models of the battery cell. That would be our truth. And then we put the error bounds around it, so you can see how that looks, and that's the corresponding error on the right. All right, so there's the algorithm in something you can actually read. There's the prediction time update, and then the estimator in the green. Those of you familiar with Kalman filters will recognize all of that. I'm not going to go through it, but just to show you, maybe to impress you, that there's really math involved here. There it is. Here's the diagrammatic version of that, right? Actual cell current informs the actual physical battery cell, and then we have the actual cell voltage, and I have a sensor out there, snapshots that. That goes down and is directly compared with what my model says. What would that voltage be if I had that exact same input coming in? Oh, it's the same. Oh, if it's the same, then maybe I'm pretty close. If it's different, maybe we have to make an adjustment, right? And I'm oversimplifying it because there's a lot of stochastics and statistics that are going into this this algorithm, but that's the basic idea that's to understand with a Kalman filter. All right, so in short, what does it do? The Kalman filter compares the output prediction to the output measurement, computes an estimator gain that weighs how much to trust the measurement versus the model. It's a trade-off, right? All right, and there's an example. So for this example, I used a state space reduced order model that I generated via using the XRA, right, the realization algorithm, subspace projection method on a full order battery cell. It handles the changing operating environment, so this is something I'm going to get into in a minute, by using something, a process that we call model blending. So one of the aspects of this model to be, or this implementation to be aware of, is that as the battery moves through its operational space, right, we have different temperatures, we have different SOCs, we actually have different sets of parameters that describe that battery cell, right? Remember, this thing is nonlinear, and here we're viewing it as a parameter varying thing. And so, how do we accommodate that as we move through the operational space? Well, the way we do it, Professor Plett talked about generating a state space model. Well, we actually generate a lot of state space models, right? We're going to do one for each of these SOCs and temperature combinations, and those are going to sit in a database. And then as we move through that operational space, sort of indicated by that blue line, I'm going to perform bilinear interpolation in order to put the state matrices back together to give me a best state matrix for that operating point. Then that will serve as the basis for my Kalman filter operation and ultimately my control. All right, so what are we seeing here? So that's a description of that. There's my bilinear interpolation. And over on the right-hand side for that model, what I'm impressing you with is the fact that this subspace-based projected model, which, by the way, I didn't mention this, I can actually generate very accurate or highly accurate results using very small orders. So that Doyle-Fuller Newman model is by nature infinitely dimensional, right? Infinite dimension. And what I'm saying, I can crunch this thing down, and I think this one was, I want to say, an 8-state model. We usually use either 5 or 8 states. Well, it's not very many. I mean, that might be like a few RC pairs on an equivalent circuit model. So the computational burden here, is not high. But unlike the equivalent circuit model, this set of numbers somehow engenders the electrochemical information that allows me to reconstruct such parameters as, on the top left is the potential, right? That's the electrode potential at the solid electrolyte boundary. That could be a very important parameter if we're tracking lithium plating, for example. And there's its associated estimation error. And down below, I have the same thing for the positive electrode. So negative and positive electrode over potentials at the electrode boundary. So those are being reconstructed from this computationally compact digital state space or discrete time state space model. All right, so not everything is easy in this world. So what are some of the obstacles to actually implementing all this? Well, the first is that the accuracy of the computed estimates, as you may have guessed, is highly dependent on the quality of the underlying model. My colleague talked about some of this, right? Do we trust the Doyle-Fuller-Newman model? Is it capturing everything that I need to capture in terms of the dynamics? And the answer is not necessarily, right? We know, particularly at what we call the boundary cases, where we have extremely high currents or extremely low or high temperatures, this model tends to diverge from reality. So we know that there are some underlying dynamic effects that are not well captured. But is it good enough? And for most regimes, we find that it is good enough, but you must be aware of this limitation. And then coming into the Kalman filter. Well, the Kalman filter looks like it, performs magic, but the magic it performs is only as good as the model I inform it with. So it turns out that if I really skimp on my Kalman filter model and I leave out some dynamics, it's going to struggle. It's going to say, I'm doing this comparative thing between the predicted output and the model output, and it's kind of never where I think it's going to be. I don't have a dynamic attribute to assign this difference to. It's going to struggle. So you have to capture all of the essential features in your model in order for your Kalman filter to work well. And this isn't, as mentioned, inherently a challenge because not all of the dynamic processes of any battery cell are well understood. And as was discussed earlier, as we get into other, down the road battery chemistries, as we talked about earlier, they're even less well understood. And so we have to be mindful of how we construct models that we're going to use for state estimation. Kalman filter does good things, but you have to inform it well. And then we have model nonlinearity, right? Full order physics-based models are inherently nonlinear. We know that. Why? Well, for one thing, we have spatially dependent diffusion that kind of drives most of these processes. We have nonlinear reaction kinetics from the Butler-Volmer equation, and then other things, some we don't understand. And so the models themselves now somehow have to capture these nonlinearities, right? We can't linearize away forever, and we can to an extent, but we're going to introduce inaccuracies if we do so. Again, nonlinear Kalman filters, like the kinds I discussed, can work really well, but they have to be carefully tuned and very carefully constructed. All right, I'm going to move on to talk about degradation, right? I think you were warned you might see that picture again. There it is. And if I'm not mistaken, you might even see it a third time. I don't know if Iker put it in his. But that must mean something. That must mean that's a really, really good picture, or it's really important or something, right? And I like that picture because when you get into this idea, this field of battery degradation mechanism, it's really complicated, okay? That's not a picture that maybe you study in detail, but you look at that and you go, wow, it makes my head hurt. Well, it's supposed to, because it's complicated. Number one, there are a lot of different degradation mechanisms, some of which we understand, many of which I think we don't understand at all, that we don't even realize are happening. So that's the first problem. There's a lot of these things. We know some of them. Secondly, they are interacting processes, right? They're largely interacting. So that means that one degradation mechanism, if it's occurring, could be influencing another degradation mechanism. One nice example of that was brought to light in a paper from, I think it was Professor Wong and his group at Penn State University several years ago. And they showed this interaction between lithium plating and SEI growth. Right? Lithium plating is this pernicious effect where, as I'm trying to charge my cell, particularly in a fast charge environment, and it's mostly a problem at low temperatures, right? I have this condition where all this intercalation is trying to happen very quickly at an electrode surface that can't really handle it. And so it sets up a side reaction. And the side reaction takes the lithium out of the ionic state and it plates it, literally plates it as a metallic material on the surface of the electrode, right? And that has two bad consequences. Number one, hey, it's taking lithium out of circulation, so my battery's not going to work as well. Number two, it's sealing up some of the entry portals into the electrode for the intercalation process itself. Now, the second one, SEI growth, solid electrolyte interphase layer, is this sort of natural formation of a layer, of a film, if you will, on the surface of the electrode that happens by way of yet another side reaction that's pulling organic compounds out of the electrolyte and so forth. And that's doing its own thing and layering up on the electrode surface. And it turns out that these two things can influence one another. In fact, what we have seen, what that paper highlighted, was that if you are experiencing lithium plating because of your charging or your temperature environment, right, it's going to accumulate over time. But if SEI growth is happening at an accelerated rate, it will eventually reach this point that's going to really trigger sort of an avalanche of lithium plating. And so this gives rise to what we call the cliff effect, where your battery has, decent performance. Okay, it's losing little. All of a sudden, you turn it on one day, and boom, this thing is not holding charge at all, right? It's the cliff effect. And so they went through this in this paper to explain electrochemically why this is happening by way of interaction of key mechanisms. And that's just one example. There's going to be many, if you put together the combinations and permutations of degradation mechanisms that can occur. Two ways that are very popular for describing the degradation of a cell or the effects of the degradation are called capacity fade and power fade. And very quickly, capacity fade really has to do with available energy, right? How much, when I charge my cell, it holds a certain amount of energy. I count on that, but over time, as you all know, that goes down. That happens for a variety of reasons. Two key reasons are loss of lithium inventory and loss of active material. Right? I talked about LLI sort of a minute ago. Occurs when side reactions are consuming lithium, taking them out of circulation. Loss of active material is different. That means the structure of my electrode is changing, and I can't really accommodate the lithium in its intercalation locations any further, because I've had some structural deformation, if you will, or inadequacy now in my crystalline structure. And so these are mechanisms that contribute to that. Power fade is a little bit different, right? Power, I'm going to talk about power and energy a little bit more later, but power fade, power is how fast I can transfer energy around. And power fade means, well, I can't suck energy out or put energy into my battery as fast as I used to, and that really has to do with the rise in resistance that happens over time. And there are many different contributors to power fade that can occur in a battery, and some of those I indicate here. And we are aware that the presence of this solid electrolyte interface, this SEI layer I talked about a minute ago, can be a high contributor to an increase in power fade over the lifetime of a battery. So obstacles here now are probably rendered obvious that we need to establish what are the dominant degradation mechanisms at play at all. Can we get a handle on those? Because they can arise from so many different factors, and some are even unknown. The ones that are known are not well understood. Obtaining a full and accurate characterization of these mechanisms is a highly non-trivial task, and I think it's going to keep researchers in business for a long, long time. So there's a lot of job security right there. Capturing the interaction among the mechanisms, right, in addition to there being many of these, they interact, and I think that's another area that is one of very active research. The paper mentioned in the previous talk by O'Kane, I thought I saw that recently, or we've actually used that. I think Eker leveraged that paper. Is probably one of the best that's made an attempt to get a handle on some of the key mechanisms and show their interactions, develop models for these, and use those in an effective way. And finally, this came out, I think, in the questions asked in the previous lecture. And this is kind of, from our view, like the holy grail of this degradation idea. Adapting the ideal cell model to capture degradation effects, right? We have this ideal cell model, the pristine cell, but things happen over time. And so we wish to adapt or change the ideal model, maybe in real time, to account for these mechanisms of degradation. So as I state here, a practical and more useful model would employ adaptive methods in some way to reassign parameter values systematically to capture aging effects. Because right now the best we can do is completely reparameterize the model after a certain interval of time and then operate with a new model till we reparameterize it again. If this could be occurring adaptively, I think it would be a great benefit. And I think undoubtedly machine learning and AI techniques are going to play ultimately a role in getting a handle on being able to do that. So another very ripe area for those interested in that kind of research. All right, my final two topics. I'll talk about two of the areas that we've spent a lot of time in our controls group, and one is computing optimal fast charge, and I'll talk about that first. And so we know that in practice, most battery fast charging protocols are really driven by what that upper voltage limit is specified by the manufacturer of a battery cell. Don't exceed 4.2 volts. Period, right? That kind of instruction. And so, okay, we'll charge until we hit that, and then we'll back off. In this section, I'm going to show you an electrochemical-based approach by applying, in this case, a model predictive control strategy to the fast charge of a lithium-ion battery. And so this method leverages things that I've already talked about. We're going to use a computationally compact, reduced order physics-based model, in other words, a PB-ROM, that's generated using our XRA, so it has all that electrochemically rich information embedded. We're going to use the MPC to impose hard constraints on certain internal cell variables in order to get the result we want. And then we're going to use that MPC to compute a stepwise optimal applied current to achieve that result. The diagram at the right shows an architecture that we use for this implementation. The gold box in the middle is a representation of the discrete time state space model. It's a little bit simplified, but it does the job there. So we have our A, B, C, D matrices, if you're familiar with that nomenclature. So that's the model. The actual battery cell is that green box at the top, right? And so the interaction here is that I have an input that drives my actual battery, and it's going to elicit some real-world output that will be measured by a sensor. That sensor that sensor measurement is compared with an output of a common filter estimator, right? That's in the blue box at the bottom, right? So that's cranking out my state and output estimate. And then that obviously feeds in some way back to the common filter, but more importantly in this architecture, it informs the model predictive control algorithm. And that's kind of hard to show you on a diagram like that, but in a very simple way, if you look at the purple line, that's showing you predictive things, right? I'm looking into the future. If I give it this input right now, what's it going to do 10, 20 seconds from now? And I'm going to use that future-looking output and compare it with what I'd like this thing to be doing in the future, and that's the MPC constrained optimization. We're going to throw constraints on things, and that's going to produce for me an optimal output. And so that's the basic architecture. I'll show you a little bit more detail here in a second. So model predictive control here boiled down to my semester-long 5590 course into one slide. Is a real-time control strategy that uses a look-ahead approach, right, to foresee what's going to happen in the future based on inputs I'm giving it now, and past inputs, of course. And I'm showing you if you just direct your attention to the upper picture at the right, the here and now is at time index k, right? So this system response came from somewhere, but it's there right now. And this piece here is what we call the prediction horizon. I'm going to look out the prediction horizon is the big one, right? I'm not going to walk all the way out there, but there it is. The short one is the control horizon. And I'm going to take a look at, if I give this input right now, what's going to happen over the course of the prediction horizon? And so my dynamic model gives me that insight. And so then I'm going to say, well, I want that output maybe to look like the straight line, right? I want an ideal step response. And so how can I tweak that input in the future control horizon interval? What can I do with those green levels there in order to optimize the performance I want over the next 10, 20, or how many seconds? And that's essentially what MPC does. There's one more complication, this is a very important one, and that is I want to do that with respect to enforcing constraints on some of these variables, right? I don't want them to exceed certain limits. And that's the real payoff from MPC. It is viewed as really the only real-time control strategy that can enforce hard constraints in a step-by-step real-time manner. And that's truly the payoff, particularly with respect to the battery problem. So as mentioned in our implementation, MPC is going to employ the linearized state space ROM generated using the XRA. Here it is in nomenclature on the right-hand side. And we have, basically, I'd point out, a linearized form of this model that pops out of the XRA. That's that Y tilde. But then I'm going to apply what we call some nonlinear corrections or nonlinear modifications in order to sort of make it a little bit more realistic towards the nonlinear form. And so that adds or improves accuracy in the overall performance. My state matrices, as mentioned before, are time varying. And hence you can see the K argument inside the square brackets. And that is a consequence of updating through the model blending or the output blending procedure that I explained earlier. And here's an example, just a quick example to show you the efficacy of this. This example came out of our book, right? So close your eyes and imagine that slide that Professor Plett presented to you that showed the red book there. That's the one I want you to buy. No, I want you to reference. So that's the book we took this out of. And what I'm showing you here is the objective is I want to fast charge this cell. So in other words, I want to drive that current to its maximum limit. That's going to be the initial limitation right there, right? In this case, it's what, 60 amps of charge current. Well, that 60 amps of charge current does this to the side reaction over potential, and MPC realizes, hey, it's going to reach a boundary. Now, the typical boundary for lithium plating is 0 volts. That's the conventional wisdom. If I go below 0, I'm going to lithium plate. In practice, it's set a little bit off of 0 for a variety of reasons. One of them to lend a little bit of conservatism. But MPC says, oh, I'm going to hit that, so I'm going to back off the current, and I'm going to make some modulations to that current, and by doing so, I'm going to hug that boundary, right? I'm not going to enter the bad place, right, where lithium plating could potentially happen. And you can see in the associated diagrams the effect that has on my cell voltage profile as well as cell SOC. And you can see as well, I did set an upper limit on cell voltage just for fun, and MPC also respected that, and it can affect multiple limits. And in theory, I can put numerous constraints, right? We've done it on side reaction over potential, lithium concentration, internal temperature, voltage. I can put a multitude of constraints, and MPC will do the best it can to optimize your objective with respect to those constraints. All right. Obstacles to this particular approach, defining the problem. Right, so the fast charge problem, if I boil it all down, it says I want to, my objective really is to introduce as much current as I can over as short a time as possible while respecting certain limits. So a couple of key questions arise. One is, exactly what quantities should we limit? And what should those limits be? In order to answer that question, I need a very comprehensive understanding of the actual electrochemical and physical processes that are affecting cell performance and lifetime. And that's where the controls engineer has to be suitably informed on the system that he or she is controlling in order to be effective. And I maintain that currently this is not a perfect science yet. A lot of that's not well understood, and it's certainly a topic for much further research for those of you looking for more things to research. Computing the optimal profile. So strictly speaking, when I talk about min time or fast charge, I'm talking about solving an optimal min time control problem. I don't know how many of you have tried to do that. That's a pain, right? That's a hard problem to solve. So instead, we have solved a related problem. The student, Marcelo Xavier, and I came up with this pseudo-fast charge problem that we published back in 2015 that solves a related problem that's much, much simpler to solve, but in the limit brings us to the exact same result in a computationally efficient manner. But I think further improvements in that computational method are an active area of continued research, and I have students right now examining different flavors of MPC and different types of predictive algorithms that can do this even better. And finally, in my final minutes, I'll talk about power limits, right? We talked about energy, talked about power, right? Energy is the ability of a battery to do work. That's the fundamental definition, right? It's the quantity of charge resident in my battery. Power, on the other hand, relates to the movement of charge, right? It's the time rate of change of energy moving in and out of the cell. And it's the power that is mostly associated with vehicle performance. Energy, how far can I drive? Power, how fast can I accelerate? How fast can I go up that hill? So the automotive industry is very interested in state of power. And state of power is used by the BMS in order to regulate the utilization of energy inside the system. And so it's a very important quantity to get right. Now, what I have found through my research is that if I can find 10 different papers that deal with state of power, I'll encounter 10 different definitions of it. And between you and me, it drives me crazy because I would like to compare things apples to apples to apples, and I cannot. And so that's maybe my pet peeve, but it's an important problem. The general term, the one I like, is defined as the amount of power on either charge or discharge that can be sustained, right, over some fixed interval of time from the present operating point, right? So that's a very good definition, I think. So for our usage, we will use that definition. I see other definitions that talk about maximum peak power over a future time interval and other different combinations and permutations of that. One, I thought, instructive way to kind of view the requirements on a state of power definition is to take a look at something called the voltage current diagram, the VI diagram. And here's one here, current on the horizontal axis, voltage above, and I have plotted on that contours of constant power. And so if I want to achieve a constant power profile for this thing, right, that I'd have to follow one of these contours. And what's obvious from looking at that, well, gee, I can't really do that by holding voltage or current constant. And so anything that assumes I'm doing a constant current, constant voltage profile to get a state of power calculation is by its nature flawed, right? I have to allow for that simultaneous change. So how do we do it? Well, we have actually at our team adopted a method utilizing the machinery of our fast charge algorithm to compute state of power. Because let's face it, we can think of this state of power as being how fast can I, suck energy out of this thing or stick energy back into it over some period of time. Well, it's like a fast charge discharge problem. So let's couch it in those terms. And what we do is we predict out over time what can my battery cell optimally achieve within a certain set of constraints. We get that energy profile, and then from here we kind of fudge a little bit because I integrate the energy to get, or the instantaneous power to get me total energy, and then I average it. Okay, so not perfect, right? But it's easy to do. So that's the engineer in me going, I need to do something expedient. It's not perfect, but it's okay. And here's a state of power example where I'm showing some examples of computing state of power using the method I just showed you. And actually, I'm comparing it to a method I didn't discuss that utilizes an even simpler bisection algorithm. And again, if you are interested in this in great detail, this chapter 8 of the book talks about this. So just saying. Okay. All right. Obstacles to computing power limits. Obviously, the ambiguity of the definition. I think it would serve the benefit, it would serve the industry well to converge on a nice standard SOP definition that we can all live with and we can all compare our techniques against. I think that would be very helpful. And then computing the SOP estimate. I think this is a great avenue for research, future research. I took one crack at it, you can see it there, but I think there are a lot of clever folks who can improve upon this, right? We can come up with better approximations, maybe even computationally more expedient, that give nice, lightweight, robust algorithms to improve SOP accuracy. I really think that's a very attractive area for ongoing investigation. All right, finally, right? BMS algorithms can be based on either empirical or physics-based models. Our conjecture is that the physics-based models are information-rich and are highly amenable to advanced control strategies that will ultimately improve performance and extend the lifetime of our batteries. There are obstacles that I presented along the lines of these 4 topics. I highlighted some of those, really talked about some more in the perspective of some future research ideas that I think are really key to advancing the industry forward. And I thank you for your kind attention and am willing to take questions at this point. Thank you.
Okay, thank you very much, Professor Trimboli. Very clear and quite a nice presentation. Thank you. And now, if you have any question, now is your turn. Is there any question in the room?
It is the perfect presentation that ends with nobody has a question.
That's it.
I have answered all the questions. Oh, I have. Okay.
Not that lucky.
Thank you for excellent presentation. I'm just wondering, these algorithms with Kalman, Phil, and so on, do you know, are they really applied in cars and industry, or are they still more academic? It's just my feeling, but Coulomb counting is used a lot for state of charge, for example.
They are applied. Yeah, they are used pervasively in industry. Not only here, but extensively in many industries. Kalman filters are very accepted now in industry, mostly linear Kalman filters. I'd say the nonlinear ones are a little bit more tricky. But yeah, you'll find good penetration of the use of Kalman filters in industry in general.
Okay. Thank you.
Yeah.
Thank you for a great presentation. I am interested in the practical implementation of these algorithms for fast charging, avoiding lithium plating. My question is around the fact that temperature is non-uniform. I already asked about this before, but I would like you to elaborate more on this, in the impact of non-uniform temperatures at pack level, so from cell to cell, but also within the cell.
Yeah. I didn't show that in these examples here. These are simplified examples, but you're right. I mean, there is a high temperature dependence. You know, a lot of these variables that we're talking about here are the parameters that Professor Plett indicated are temperature dependent. And so you will have different temperature or different parameter sets that are associated with identification at a particular temperature. And so those would be built into the family of models that we would use in this blending technique. And so as we move through the operational space in this particular implementation, notice I had SOCs, I think, on the horizontal, and then I had temperatures. And for a given temperature SOC operating point, I would adopt a new model that adapts to the temperature that is estimated to be at that point. Now, the question becomes, how do I know what the temperature is right there, right? And that's a good question. Ideally, you would have cell-level temperature measurements. And we have done some simulations where we have, I didn't show it here, but we can use the same Kalman filter machinery. For example, if I have a good thermal model and I have an external surface-mounted temperature sensor, which would be the most practical, that I can come up with an accurate and trustworthy estimate of what's going on at the core, which would be my limiting. That's the one I really want to know about, right? If I could have a core or a surface temperature, of 30, but a core of 50 C, and that would be problematic, let's say. And so I can use the Kalman filter to drive that estimate, and then use this control methodology to put a constraint on any behaviors that are bringing my temperature into that operating regime. Of course, it's expensive to put temperature sensors everywhere, and maybe that's not engineering or economically wise. And so now we have to think about, and that's why one of the reasons I was asking about smart sensors, right? How can we do a better job with fewer sensors and come up with accurate estimations of what that temperature environment is, maybe around a cell or a cluster of cells, in order to affect effective controls like this?
Yes, thank you. And elaborating more on that, in my former research group at Imperial College with Professor Offer and Billy Wu, we have worked a lot on thermal management and thermal modeling, and we figure out that it's possible to actually design cells in a better way for thermal, well, I would say for temperature homogeneity. So actually the cells can, maybe you lose a little bit of energy density, but not that much, but actually you can improve the thermal behavior. But I don't see that this is happening yet, but I think this can be a solution for problems like that. So yeah, maybe for problems like this, my feeling is that we need to think from the big picture, or from a high-level perspective, and think about combining software solutions with the hardware, actually. Yeah. What is your feeling about this?
No, I think you're right on. I think that is a really, that's a really sensible approach. And I think we do have to, again, I think as an engineer, so we meet in the middle somewhere, I don't think we can always get to the optimal place using software solutions. And we have to sort of mitigate some of that gap by the hardware redesign, like you're talking about. And that's a really good example. If we can maybe homogenize the thermal environment or the temperature distribution in a cell, that sort of reduces the computational burden that I'm talking about of having to, strictly model great gradients or something like that in temperature. So I think there's a lot of promise there.
Okay, thank you.
Yeah.
Is there any other question?
Hi, Professor. Thank you for the presentation.
Sure.
It's really nice. I wanted to ask you, in practice, what type of blending approaches do you think it's best suited?
What type of, I'm sorry?
Blending approaches, for like the model blending. So like what type of weighting functions do you think is like best suited for that?
So in the blending techniques that I presented here, we actually implement two different types. So as I described, if you look at the points on that grid, if you can imagine that grid, each of those is a separate ABCD set, right? And so I'm basically, as I move through the operational space, I'm going to find the 4 points that are the closest to my operating point. And then I'm going to perform literally a bilinear blending. It's a straightaway, it's nothing super fancy, just a straightaway bilinear interpolation. Now we could use, the cubic functions, we could use other things in order to do that, but this is computationally simple, and from what we've seen, provides very nice behaviors. One thing I would point out, when we started down that path, we did something called model blending, where basically we took the A matrix itself, and then we tried to blend that, with the A matrix at an adjacent point. And if you're familiar with this kind of thing, what happens is you may not retain the continuity in the eigenvalues, and you'll get reshuffling of those things. And so that could lead to some transient dynamics. And as if I was to show you an example there, I think we have some in the book, you'll see these transients actually as we go from one model to another. As a mitigation of that, we went to something called output blending, where instead we blend the output values themselves after they're produced by the model. And that smooths out that behavior. But that was again, I think there's another research idea, room for improvement there. I firmly believe there's a way we can properly stitch those eigenvalues and mitigate that transient. Haven't figured it out yet, but maybe you can.
Thank you very much.
Okay.
Okay. Professor Trimboli, one last question from my side. What do you think about you talked about the fast charging, but what are the new trends? Do you think that we will see like more static ways of charging a battery, like, I don't know, maybe pulse charging, but static, or something more dynamic depending on the state of the battery, the temperature? What do you think about that?
Yeah, there's a lot of interesting research going on there right now, I'd have to say, and maybe Iker will talk about some of that in a few minutes. But we have seen some evidence experimentally that, if you recall, the sort of fast charge profiles I talked about here are very continuous, right? They're, as you would expect. But there's some evidence to suggest that, our model of lithium plating, that we have adopted so far is a little bit incomplete, right? I talked about lithium plating, this lithium metal adhering to the surface of the electrode, but what I failed to explain is that there's another mechanism where lithium can strip back off the electrode. Okay. So maybe this isn't a permanent failure of my electrode. Maybe I can recover something. And so there's some experimental evidence that shows if instead of a constant charge current, I did a pulse of charge-discharge of some strength and some duration and some duty cycle ratio, that I can sort of optimize this plating stripping phenomenon to allow me even faster charging. I can actually charge in environments that I could not fast charge, say at low temperatures or something, where I'm very inhibited in terms of fast charge. Maybe this can allow me to, allow a little bit of plating, but then strip most of it off, and in the net, I'm gaining a faster charge. So I think that was really exciting to me when I saw this in experiment, and then Iker kind of landed onto a resultant simulation that I found very intriguing. So I think there's potential there for sure.
Mm-hmm. Very, very interesting topic. Thank you very much.
Okay, thank you. Thank you all.
And now, it's a pleasure for me to introduce my colleague, the brand new Dr. Iker Lopetegui. He's going to talk us about mitigating lithium-ion battery aging, physics-based aging diagnosis, prognosis, and control. Iker received his bachelor degree in energy engineering, master's degree in energy and power electronics, and PhD degree in applied engineering from Mondragon Universitatea. He presented the PhD 2 days ago, so that's why he is the brand new doctor from here. He is currently a researcher at Mondragon Goya Eskola Politeknikoa. His research interests include lithium-ion battery modeling, state of health estimation, aging prediction, and control strategies. Current research efforts include physics-based reduced order modeling for lithium-ion batteries, physics-based battery aging modeling, state estimation and health estimation of lithium-ion batteries, and degradation-aware control strategies. He will be presenting his work. And Iker, please, the floor is yours.
Okay, thank you very much, Eric. Okay, so, well, Eric, thank you very much for the kind introduction. So, I titled this presentation, well, in a very similar way as my PhD, but actually I'm going to talk a little bit more about what we are doing in our research group, not only my personal work. So, these are the the contents that I'm going to follow. First, I'm going to go through the introduction, what are the main objectives of our research group. Later, I will talk about battery aging and how we can use battery aging models to predict this aging behavior. Afterwards, I will go, again, through state estimation and aging diagnosis. And I will finish the presentation with the work that we have done in control. So let's start with the introduction. So in our research group, we want to ultimately improve battery usage, principally lithium-ion battery usage. And there are many reasons to seek better control. So one of them could be safety of our lithium-ion batteries, since it is a really hot topic, and every time we see a battery explode, we see it in the news. So our approach is that, manufacturers give us a fixed safe operating area that previously Dr. Varela talked about. Our belief is that the actual safe operating area of the physical cell could be different depending on its state. So depending on this diagnosis, we could maybe contract more the safe operating area of our battery, depending on these electrochemical estimates. So another very important control objective is also to reduce battery aging, and if possible, while maximizing power and energy capabilities of our cell. So, as I already mentioned, our focus is on physics-based battery models, and why is this so? So first, because we can predict really interesting physical information, which could be used also for internal state estimation to, as I said, improve safety. And also, we could implement more advanced control to limit this battery degradation using physical knowledge. So the most well-known physics-based model is probably the P2D model that has been already mentioned. It predicts these 5 variables that has been mentioned, the concentrations and the potentials on both phases, the electrolyte and the solid phase, and the lithium flux interacting between both phases. So one approach to overcome the computational burden of the P2D model is to simplify actually the P2D model, making some extra assumption, as they have already said. So the most used model probably is the single particle model, but it can face some limitation due to the assumption of a single particle and neglecting also the electrolyte dynamics, so it loses accuracy at mid-high current rates. To overcome this, a single particle model with electrolyte has been proposed in the literature in many articles, and this certainly improves the prediction capability of the single particle model. So, as they have already presented, physics-based models have many challenges, I would say. So one of them is the computational cost. We have these partial differential algebraic equations that are really hard to solve. Maybe we need numerical techniques, and therefore we need some kind of simplification or model order reduction. Another big issue, and probably the most important one, is the parameterization of these models. So obtaining a good set of parameters is extremely challenging, and we sometimes require destructive tests, which are time-consuming and expensive. So this is, of course, a huge burden for these models. So one approach to overcome the first challenge that we have is the model order reduction. So model order reduction these techniques have the objective of reducing the computational complexity while maintaining or at least minimizing the error that we are committing when this reduction happens. So there are many different approaches, such as spatial discretization, like finite element method, finite difference. There are others that are function approximation methods, such as the Galerkin approximation, the orthogonal collocation, and so on. And we can also find some frequency domain approximations, like the Padoe approximation or the realization algorithms that Professor Trimboli and Professor Pled mentioned. So we did a literature analysis in my PhD thesis in order to define which reduction technique was actually the best one for our purpose. So here we can see that there are many different techniques, and we have identified some key performance indicators to analyze this literature comparison. So the first feature is the model reduction technique analytical or numerical? So this is really relevant for my research, since I was trying to adapt the model parameters that changed with aging. So I wanted to have my parameters in my reduced order model expressed symbolically, so that I can alter the reduced order model quite easily, let's say. Another important factor could be the computational time and also the memory requirements that it has. And also, well, the modeling accuracy is also a crucial factor. So seeing all this, we choose the orthogonal collocation method, which is a function approximation method. It's based on using a set of approximation functions in order to approximate in the best way as possible the original partial differential equation that we had. So here I show you some different results that we obtained using the orthogonal collocation method in these three different models: the single particle model, the single particle model with electrolyte, and the P2D model. So as you can see, well, here I plotted some results for a high energy cell and some other results for a high power cell. This was important to me because when I started my PhD, I read a lot that the single particle model, or even the single particle model with electrolyte dynamics, couldn't perform well at mid-high C rates. So here you can see in a high power cell that the single particle model with electrolyte dynamics can deliver almost the same voltage prediction as the P2D model. So it depends a lot on the parameters that we have in our model, on the type of cell, the thicknesses of our electrodes, the size of our particles. So this is not just an easy question to answer. So from this comparison, we saw that, well, the P2D model obviously is the most accurate model, but the single particle model with electrolyte dynamics does a pretty good job. And it reduces the computational cost a lot, and also avoids some convergence issues that we can have in the P2D model, since we obtain a differential algebraic equation system that is actually really hard to solve. So as I said, well, the main issue, or for me at least, is the parameterization of these models. So we have here in our university a PhD of Clara Rojas, directed by Unai Iraola and Laura Oca, that is focused on obtaining a set of accurate parameters for this type of models. So her approach was, well, seeing the identifiability issue that Professor Pled presented, we saw that we can actually measure some parameters of the model quite easily. Well, I say easily, but I don't know how to do it. And we also have some problematic parameters that, even if we know how to measure them, like Laura or Clara, we have a lot of uncertainty and a lot of variability in our results. So it could be better to use some kind of optimization technique, maybe. So they had this idea, which was based on, well, we will use a mixed methodology with some invasive, some destructive tests to obtain these parameters that I am certain of, and then I will optimize the rest of the parameters doing some clever testing in the laboratory. So for that, she uses some sensitivity analysis to identify which tests are the most optimal to define some certain parameters, and well, it does other tests to determine others. So it kind of simplifies the problem. So this was a nice figure that she got with the different parameters that she can measure with certainty, and then she has some parameters that she optimizes using well, different testing procedures and different approaches. And also, she included a thermal model, a thermal characterization procedure, also based on some invasive, some experimental tests and some optimizations. So the research areas that we are developing around physics-based modeling, we have first what I have presented already, the simplified and reduced order physics-based models with different parameterization techniques. Then we would also like to somehow do aging prognosis. So we want to be able to predict how our batteries are going to be aged in the future. And also, we will like to diagnose our aging state inside the battery and determine how our battery is behaving. With all this information, finally, we would like to, as I said before, improve the battery usage and design some kind of degradation or control strategy to improve fast charging algorithms, for example. So regarding the battery aging prediction part, so as end users, we see different in our different devices like smartphones or electric vehicles that we suffer some kind of capacity fade, where I have less usage time, less range in my vehicle, but also I see that we have this power fade. So I have less acceleration capability, increased temperature in my phone when I charge it, and so on. But actually, again, this nice picture. So what is happening inside our lithium-ion battery when we see this kind of aging effect? So as they already said, this is a really complex matter. The different mechanisms have a lot of interplays between them. We know more or less how to model more or less accurately, I would say, some mechanisms, but we are not even aware of many of them for sure. So in order to predict this aging behavior, we need some kind of aging model, which we basically differentiated between empirical models and physics-based models. So empirical models, as you may know, are based on collecting a lot of data from the lab and then mimicking this capacity fade or power fade behavior with some equations. And on the other hand, physics-based models go through the physical part, physical knowledge of our battery, and use some physical equations to predict this specific battery aging behavior. So in our research group, we prefer to use physics-based models since we think that they can give a lot of physical insight that we can use later to control our batteries. So here I show this picture where I showcase the different aging models that we have implemented in the P2D model and as well in the single particle model, such as SEL layer growth, loss of lithium inventory, loss of active material, and so on. And now that we have talked about these physics-based approaches, okay, how should we implement these models actually? So which kind of model should I use to model this capacity fade or power fade? How do we obtain the parameters of these physical equations? And how can we ensure that they are going to predict the actual mechanisms well? Well, our belief is that we could help ourselves with some degradation mode estimation data. So here I show a lithium-ion battery normal operation. So we have the negative and positive electrodes in normal operation. So we have this intercalation between them. We have more lithium inside some electrode. We have less potential. Okay? So when we have some kind of loss of lithium inventory, some kind of side reaction, such as CI growth or lithium plating, when we are charging the cell, we are deintercalating some lithium from the positive electrode. So we are, well, the positive electrode potential is going up, but since the lithium is not being intercalated in the negative electrode because it's being deposited in a passivation layer, we have this kind of shift. Okay? And the loss of active material model, actually, what it does is, well, it reduces the amount of capacity that we have to accumulate lithium in our electrode. So this produces a shrinkage in the OCP of the negative electrode in this case. So these effects affect the OCV of our cell. And with some optimization techniques, we could be able to see this type of degradation and estimate this degradation information from this data. So with that, we believe we can use this information for the characterization of our models, but also for the validation of them. And we can, well, we can have additional information to the capacity, fade, and impedance increase information. So this estimation tool was developed by Sergio Fernandez. It uses a genetic algorithm approach to reduce, as I said, the open circuit voltage error, tuning the shift and capacity of each electrode. So with this information, we have, I will say, a new modeling approach, which objective is to accurately predict battery aging behavior with a reduced number of experiments. So in the end, what we want to do is just to make it cheaper. So for that, let's say we have this degradation mode estimation data from our optimization tool, and we see that our battery is aging with some loss of lithium inventory amount and some loss of active material in both electrodes. So this tells us that we cannot use just an SCI growth and lithium plating model to predict our aging behavior, since we also have some loss of active material in the negative electrode and in the positive electrode. So this gives us additional information and additional reliability in our physics-based models that only a capacity-based or only an impedance-based fitting does. So also we can fit these parameters of the models with this additional data. So with this, we have some preliminary validation results using an SCI growth, a lithium plating, and loss of active material model. And here you can see that we were able to predict loss of active material in different conditions and loss of lithium inventory with relatively good accuracy, I would say. I'm saying these are just some preliminary results, and these cells are not sufficiently aged to claim this like an good aging model, but we are on our way. So regarding the state estimation and aging diagnosis part, first I will talk about the state of charge estimation using these physics-based models. So a state of charge is actually a kind of measure of the state of lithiation of our electrodes. So if we have this brand new cell and we know the parameters and we know the state of charge, we can actually know the state of lithiation of both electrodes. However, when we have this kind of shift of or shrinkages of the negative and or the active material, sorry, and we have this loss of lithium inventory. This OCV curve will finally change, and this will make our model confused, and we will have erroneous state of charge estimates since we are not able to accurately model the OCV of our cell. So in order to perform our state estimation algorithm that I developed in my thesis, we used the single particle model with electrolyte dynamics. So here I put the equation, well, the voltage equation of this model. So as you can see, it has many terms that we have to estimate from just one voltage measure. And these are the state variables that we have to obtain from that voltage measure. So this leads to a weak observability problem. So in order to analyze this weak observability, we used a method called the Lie derivative method to obtain the observability matrix of our system, and analyzing the condition number, we could see some issues regarding the electrolyte, or sorry, the estimates of the concentrations on our model. So in order to improve that, we analyzed the individual observability of our states, which are the positive electrodes, negative electrode, and the electrolyte concentration. So here we can see that the condition number reduced a lot for all the cases instead of the electrolyte concentration, where we have some issue when we have a 0 ampere current in our cell. So with this approach, we are somehow improving the observability of our state of lithiation states of our electrodes, and also the observability of the electrolyte concentration. So seeing this, there was a very nice publication in the literature from Alam and Honori from Stanford. They used the fact that we have better observability if we analyze the states individually from our cell voltage, and we kind of leave the rest of the states in open loop. And therefore, they used a single particle model without the electrolyte and estimated both concentrations of the electrodes. And they saw that they got very good results. However, we saw that they did not include the electrolyte dynamics in this analysis, and we thought this was an important state also because it could affect in some variables like lithium plating, for example. So for that, we have designed a new state estimation algorithm which interconnects 3 sigma points Kalman filters. And this way, we should be able to improve the observability of all our states and then have a correction in all of them with this estimator. So these are just some results that I obtained. So here, as you can see, we have initialized all the state variables from an incorrect point. And as you can see, they correct the estimates pretty well. And the only variable that takes a little long is the electrolyte concentration due to its lower sensitivity to the voltage equation, as we have identified. And with this, we can perform a very nice state of charge estimate, at least in simulation. So once we age this cell, of course, our parameters will change, and we'll have some degraded battery cell. So I did a comparison in my PhD document that is that, well, stating the state of health of the battery with the capacity of the cell is kind of estimating the health of a person using its age. So I know this woman from my town that I thought when I was a kid that, well, she must be like 100 years old. And now I look at her and I'm thinking like, well, she must be like 70 years old. So I don't know what's happening in there. She has some kind of sublinear aging trend. So the thing that I want to say is that, well, if we are using physics-based model, we must estimate somehow some additional aging information. Okay, so we have to determine, is this really a really aged person with a bad health, or is this woman from my town? So for that, we designed a new method taking into account that actually the loss of active material estimates and the loss of lithium inventory affect the actual open circuit voltage of the cell. So they also must be kind of observable from the cell voltage data. So we have estimated all these parameters that are from the physics-based model. And as you can see, we got some very nice results in simulation. So with all this, as I said, we can obtain some degradation mode data that can improve the diagnosis of health that we are doing in our cells. So with this, of course, we want to correct the state of charge and internal variable estimates. And as you can see, at the beginning of the cell, when we have the incorrect set of parameters, the estimates will suffer a little bit. They are not that accurate. But once the parameters are corrected, the state estimates are corrected very well. And with this also, of course, we can obtain a state of health estimate based on capacity too. So here, I'm going to talk a little bit about, well, the artificial intelligence work that we are developing. Well, Josu is developing in his PhD. So we saw that artificial intelligence can be a very good tool for state of charge and state of health estimation, but they kind of lack interpretability. So we don't want to use those models alone in order to improve control, since they cannot give us very reliable information, I would say. So for that, Josu's approach is to combine this interpretability that physics-based models have and also the adaptability that machine learning algorithms have to kind of get a new approach based on physics-informed neural networks or some other approaches. Okay? And with this, we wanted to tackle the problem that we have with the parameterization data. So as we know, there are no two cells that are equal from one another. So even if we do a really great parameterization of our cell, if we buy a new cell from another batch, or even we try a cell from the same batch, the parameters will be probably slightly wrong. So we thought that, performing the same kind of sensitivity analysis that Clara does for her work, we could somehow select the appropriate data that we could use to fit some selected parameters that are sensitive to that data and perform this kind of optimization of the parameters online. Okay? So we could correct the different parameters of different cells online. So this, coupled with the state and parameter estimator that I showed you, could be a possible solution to the parameterization issue that we have. So first, we have some set of accurate parameters for some cells, but we could be updating them with aging and also, different cell characteristics. Okay. So once that I have talked about physics-based battery modeling and also how we can predict battery aging, as well as how can we diagnose our aging in the battery, I want to present you the work that we have done in developing new control strategies. So for that, we have focused on the fast charging problem. Here, there are different methods, active methods, which are more focused on actively estimating the states of the battery and using some derating in the current or things like that. And we have also passive methods, which are based on optimizing current profile offline and then using this current profile in the cell at any condition. So here, these methods have the benefit that they can use more complex models since the computational cost is not a critical fact. However, we prefer to use active methods since our estimation tools can give us very important information to develop correct derating strategies. For that, we have used the model predictive control, which can handle constraints, and it has a nice predictive ability that where we can use the aging models that we have developed before. So, as I said, lithium plating is one of the most critical mechanisms in fast charging, but also we cannot forget the thermal aspect. So, in order to perform some simulations, we included a thermal model in our single particle model with electrolyte dynamics model. So, we used the same cost function that Professor Trimboli talked about, which was adopted from this publication. And also, the developed lithium plating model for our cells was used to evaluate the simulation results that we got. So, the first approach that we adopted is, well, let's maintain the overpotential above 0, since this way we can avoid lithium plating. Okay? And we got these results. And I was surprised to see that our lithium plating model, which is the plating model that before Professor Plett and Professor Trimboli referenced from this work by O'Kane, was predicting some lithium plating still. And, well, here, comparing with the normal CCCV charge, it reduced only by 10% the amount of dead lithium, so the amount of lithium that we have lost. Additionally, we also saw that, well, this kind of approaches inevitably make our charging time a little faster, or a little slower, sorry. So our approach was to, well, why don't we use actually the prediction information that the lithium plating model is giving us in order to, actually control the current with this information. So for that, we inserted a constraint on the plated lithium amount. So with that, we managed to obtain, I repeat, just in simulation, a faster charge and a lower dead lithium amount than in the 2 previous cases. So these are very promising results, in our opinion. However, of course, we need more experimental validation to analyze more this phenomena. So thinking more of a safer charging strategy, we thought, well, maybe we can constrain even more the amount of plated lithium and perform a safer charge with even less lithium. So with this, we managed to make our dead lithium amount around 1% to the dead lithium amount that we were obtaining with the fast charging constant current, constant voltage profile. So these were great results. Finally, we have different future project or plans which are, well, related to including state estimation with the degradation hour control algorithm that we are proposing, implementing them in the experimental part. Also, we could try to use different degradation mechanisms, such as, well, if we see that our cell is suffering a lot of loss of active material, maybe that's something that we have to take into account if in our derating or controlling strategies. And also, we could add multi-objective cost functions, or yeah. So this was my presentation, and thank you very much.
Thank you very much, Iker, for your presentation. Now, if there's any question in the room, we still have time.
Hello. Yeah. So I'm a newcomer in this field. So maybe my question is stupid, but so the question is about the identifiability problem. So yeah, it was in the beginning of the. So the thing is that the problem of parameterizing is finding experiments for which the given parameters are sensitive, let's say. And, well, in this presentation, you claim that this helps with the identifiability problem. But from what I understand from Professor Plett, so the identifiability problem is more in the equations, let's say. It's more in the fact that you have to lump parameters together in order to have some, it's not that moving one parameter up or down.
Yeah.
Makes it, so I wonder if, because until today I understand it like this, like what you present, but I'm not sure now.
No, maybe I didn't explain it okay. So the sensitivity analysis is more to determine which kind of test we should use to characterize some parameters. As you say, the identifiability problem, well, Clara is trying to solve it using some physical experiments. So with these experiments, she is trying to determine some set of parameters, and then when you have these parameters determined, the rest may be identifiable. Yeah.
Yeah. Okay. So in the physical models, these parameters are actually go one by one in the different expressions. And the rest are, let's say, physically, you open the cell and you measure it. Okay, yeah. Thanks.
Thank you.
Okay. Is there any other question? Jorge, you have a lot of questions today.
I have many questions. I can tell you many things. Thank you for a great presentation. Well, today we have been talking about this identifiability problem from the perspective of how mathematically we formulate equations, and also from the perspective of calibration tests or characterization tests, as they are called sometimes. But I am interested also from the perspective of validation. So when you want to validate the model, because, well, at the end of the day, you also need to differentiate the contributions in terms of aging in this case. And this is not easy to do. Well, maybe you can elaborate more on that.
Of course, yeah. The validation problem is, well, also one of the big problems of these models. Well, Professor Plett said, are we actually believing the models? So our approach, at least in the aging modeling part, was to, well, at least if we know that some aging mechanisms are taking part at, well, let's say high currents or low temperatures like lithium plating, or when we discharge fast the cell. Well, if we hadn't have that knowledge, and also we have this degradation mode estimation, with this information we cannot know exactly which mechanism has happened, but we know what they have produced. Like, did they produce loss of lithium? Did they produce loss of active material? And does that correlate with the capacity fade and our mechanisms that we are modeling? So it is not perfect, but it is some kind of, yeah.
Yes, because there are hypotheses over there. Do you think it could be interesting to include more sensing, prepare cells particularly for that? Maybe because, well, this can also change the result. This is a tricky thing. Or maybe with destructive analysis, post-mortem, I don't know.
Yeah, of course. I mean, more sensing could help a lot. Well, because it would add more observability in what's happening inside our cells. So maybe like a reference electrode, pressure sensors, things that we have commented. We are also using some kind of heat flux sensor so that we can analyze the heat that is going in and out of the cell. So this kind of additional information, of course, gives us a lot of more information. Yeah.
Thank you.
Thank you.
Okay. Is there any other question? Yeah, up there.
Hi, thanks for your presentation. I would like to talk a little bit more about aging mechanisms. I have been reading so much about them, and I have seen that what Professor Plett also said, that we are like, it's mandatory to do the invasive methodology to know the electropotential curve, for example, and then, as you said, to perform a DVDQ analysis and obtain those degradation mechanisms, one for LLA, another one for LAMA, and this kind of stuff. But could it be possible to avoid this kind of invasive and, for example, do DVDQ analysis like for the OCV curve of the full cell, and then apply some like characteristics to know which kind of degradation mechanism is happening in a way and which one in the other? Because I have been talking with some colleagues about that also, and they are a little bit, I don't know how to say, they are confused about if it is going to work or not. So.
Yeah, of course, that's actually a hot topic. Well, I think that, as Professor Plett said, it's kind of difficult to avoid the physical testing and experimental part of the half cells. If we take that out of the equation, I think we can have a lot of information from the outside. As Dr. Varela said, with additional sensing, DVDQ analysis, incremental capacity, and electrochemical impedance spectroscopy, there is, I think, a lot of information that we can get with these methods. And yeah, having a little physical knowledge and relating this to the experiments or the results that we are obtaining could be done, yeah.
And do you think that, for example, a method that is applied to use in half-cell modeling could be applied with a full cell analysis of DVDQ curves, for example, like mixing models? For example, if a model wants to use half-cell electropotentials, but you don't want to use them, like use OCV curve, like half and half or something like that, or like dividing, like on your own way, the OCV curve?
I think that's difficult task because, well, if we get the OCV, in the end it is the positive electrode potential minus the negative electrode. So it's the same identifiability issue that we have. So it's kind of difficult. Maybe we could use, I think I've read something like we could use temperature sensors to identify the negative electrode DVDQ curve. The incremental capacity analysis also could help in detecting the negative and positive electrode plateaus. Yeah, I don't have a sure answer, but maybe it could be done. I don't know.
Okay, thanks.
Thank you.
Okay, anyone else? Nothing? Okay. Okay, after these two interesting presentations, let's take a break and eat something in the hall of the building. But first, we will take the picture here because outside is raining. So come here. Hello again. Now we are facing the last part of this event, the last 2 talks. And now I have the pleasure to present one of our brand new PhDs, Xavier Dorronsoro. He is going to talk us about his thesis towards enhanced battery systems, modular hardware, and control. Okay? Xavier received his bachelor degree in energy engineering, master's degree in energy and power electronics, and PhD degree in applied engineering from Mondragon Universitatea in 2018, 2020, and 2024, respectively. He is currently a researcher at Mondragon Goya Eskola Politeknikoa. His research interests include lithium-ion battery modeling and control strategies with a special focus on modular battery management systems. Current research efforts include battery system architectures, modular battery management strategies, predictive battery management, and degradation-aware battery control strategies. He will be presenting the work that they are doing in their research team, reading modular battery systems with a special look not only at hardware level, but also at control strategy level. So, Xavi, the floor is yours.
So thank you, Eric, for this kind presentation. Okay, so before the lunch, we have been mainly talking about battery modeling and cell parameters and so on, but now I would like to bring your attention to system design and how to manage, let's say, battery systems, not just at cell level. So this is the index that I'm going to follow during this presentation, just with a brief introduction on the problematic that we identified. The new trends in the related to battery architectures, then the design or the prototype that we are currently developing, the power distribution strategy that we have formulated during my PhD, and I will finish with the conclusions and the main future lines that we have defined for the next months. So, we all know that we are nowadays in a critical environmental situation, and in order to transition to more sustainable models, renewable energies, as well as electric transportation systems are considered to be key. And battery energy storage systems are gaining, or they are already considered a key vector. So, nowadays, there are many different research lines related to batteries. We have many researchers working on new battery chemistries. Then, as we have seen, they are trying to improve battery-related monitorization. We are also looking for better management strategies, and we would like to optimize then the design of a battery system in order to maximize their performance. So the main work that I have been doing with my research team is related to battery management and the system design. So nowadays, the battery, medium and large size battery systems are based on a modular configuration. So then the basic concept of the module is scaled up to the application requirements using serialization and parallelization. But of course, we have to always include a master controller and the power converter system in order to connect to the application. But in real-life systems, we always have cell-to-cell variations. So we can suffer from unequal degradation between the cells. We can suffer also from having weaker cell limitations and reducing the accessible energy. So external balancing circuits are included in order to somehow mitigate these heterogeneities. And as we have a fixed dimension of the battery system and it's not fault tolerant, we'll have to replace the whole system in case there is a failure. So we have seen that there are new trends in order to somehow reduce these limitations that the conventional battery system shows. And on the one hand, we have the reconfigurable architectures, and on the other hand, we have the modular battery systems. So regarding the reconfigurable battery systems, the most basic concepts are based on using a switch in order to control the cells that are connected in parallel, or including 2 switches per cell in order to be able to handle the cells or in order to be able to handle the output voltage of the module. However, in the literature, you can also find many other examples using up to 6 switches per cell. So this way, we are able to access more energy when operating the battery, and the fault-tolerant, we can also apply fault-tolerant control strategies, but the complexity is much higher due to the amount of electronic components that we have to add at the system, and the efficiency may decrease when we operate at higher power rates. So then it is also possible to control the cells, but instead of in a reconfigurable way, but just by controlling individually using a power converter. And in these cases, we will be able to obtain higher accessible energies. We will be, of course, improving fault tolerance, including fault tolerance control strategies. We are able to somehow formulate some flexible system design strategies, and we are enabling the use of heterogeneous battery systems. However, if we want to control each cell individually in a medium or large size battery system, this becomes really complex and the cost can increase a lot. So in the literature, there are also some other examples where they don't control each cell individually, but they create somehow groups, creating modules with different number of cells. But again, we can here suffer cell-to-cell variations that may limit the operation or at least the available energy of the whole battery system. So in order to understand the advantage, or just one of the advantages of the modular systems, we perform an analysis taking into account these cell-to-cell variations. So here in this graph, I'm going to show you how the accessible energy, depending on the kind of battery configuration we have, can change according to the standard deviation of the system. So first of all, we have the system where all the cells are connected in series, and we have a dissipative balancing strategy. But then, if we divide all these serialized cells into smaller modules, we can see that the minimum, that we are able to somehow increase this minimum available energy related to the battery system. Then we extend this analysis to circuits with active or non-dissipative balancing strategies, and we have seen that we are even able to improve the results that we obtained previously. And of course, if we try to control each cell individually, we will be able to get the best result, but again, we will have to invest more money and the system will become extremely complex. So, taking this into account, we decided to focus on the modular configuration, and depending on the application, for example, in consumer electronics, it's enough having just one cell, but in some other applications, such as the distributed generation or the data centers, we have to scale up this system and we have to increase the complexity. A question that many times appears, and that they asked me yesterday, the members from my jury, is, okay, and what about the cost? Because if we are including more power converters in the system, everyone at the beginning thinks that the cost will be higher. So having a look at this figure from the National Renewable Energy Laboratory, when we talk about residential application, it's true that power converter systems has a really high economic cost, and that they are even similar, or the cost is similar to the one corresponding to the batteries. But if we talk about commercial case studies or utility case studies, power converter systems are much cheaper than the battery systems. So the cost will not change that much. So definitely, we can consider that using modular battery energy storage system in these medium and large size applications could be interesting. Then we have to take also into account that these modular batteries can be coupled to an AC system or to a DC system. So we can parallelize these modules, or another architecture that is gaining attention in the currently is the modular multi-level converter that is based on the serialization of the modules, especially for high voltage applications. And regarding the DC systems, we can parallelize these modules, or we can also serialize them. And of course, we can somehow mix also these both architectures. So our objective is going to be to design a modular and scalable battery energy storage system, but based on DC solutions. So here you can see the picture of the system that we are currently trying to build up. And the prototype nowadays is based on a system where we have the cell monitoring system, where we also included the dissipative balancing strategy. Then we have the Texas Instrument Launchpad, that is a really economically cheap solution, and where we are able not only to use equivalent circuit models and semi-empirical degradation models, but also we have been testing the physics-based models that Iker introduced us before. And we are able also to perform the DC-DC converter control with this same Texas Instrument Launchpad. Then we have also the converter. In this game, we are focusing to transfer the power with a high step up in order to somehow prioritize the higher controllability that the parallelization of the modules offer us. So, as I said before, we have higher controllability with parallelization, but we struggle from voltage amplification because in most of the cases, the power converters present reduced efficiency. However, and in the other case, with the series configuration, we have a lower controllability, but we don't struggle that much because we are able to operate at higher voltage scenarios with higher efficiencies. So, as I said before, in our case, we will focus on applying new control strategies for modular battery systems. And in this case, as the parallelization offers us more flexibility, we are going to focus from a converter point of view in developing a high-gain DC-DC solution. Regarding the control system architecture, there are different options in the literature. The most extended one is the centralized one with higher controllability, but here we can struggle if there is a failure because the whole system may shut down. The other two options are the decentralized one and the distributed one, and these two options are more robust to any failure, but they are more complex to be developed. So as the objective of our work right now is not developing or just testing these kind of control architectures, we are just focusing on centralized solutions. And for applying these control strategies, we decided to use this commercial solution, the Raspberry Pi. And here, with this solution, we would like to connect the Raspberry to the cloud to enable data logging, to be able to somehow update the battery models that we have in the system. We would like to be also able to somehow predict the incoming states and ensure the safety of the battery system and also of the power converters. Then this central controller is also important because it will be always controlling the battery in this way, taking aware the different states and that may be used as reference for the control. So now let's have a look at the power distribution. That is the main contribution for the literature. So here, if we consider a modular battery system with just the parallel configuration, we are going to focus then in the intermodule level control. So we assume that the intramodule level control will ensure the correct operation of the cells that are in each module, and the application-oriented control level will define which is the power demand that the whole modular battery system has to supply to the application. But in this case, as I said before, we are going to work with the intermodule control level. So when we define a control for the batteries, we have to take into account that there are multiple variables that can be considered, some of them related to the battery system, such as the state of charge or the temperature, but there are also some other variables related to the application, for example, the cost. We can also take just one objective into account, or we can somehow mix multiple variables, formulating a multi-objective problem, and then we have to also choose which is the control algorithm that we are going to apply in our control solution. So the most extended one nowadays is the rule-based, but machine learning is gaining momentum, and as Professor Trimboli already introduced us, the MPC is also a really interesting tool. So, to these control strategies, when we apply these control strategies, we have to take also into account that somehow the battery aging rate has to be limited. So nowadays in the literature, it is really extended the solution that is based on establishing certain constraints to the battery and using them along the whole life of the battery, but some other solutions are beginning to update these constraints during the lifetime of the battery. Then we can take into account if we are, or we can distinguish the option where we use the battery model to operate the battery system, or we just apply heuristic methods where the operation is simplified with a general knowledge that we have generated from the previously done experiment. So, in our case, we decided that even if they are the most complex one, the highest potential is presented by the model-based dynamic derating solutions. And having introduced the control strategies, the details related to the control strategies, our approach is going to be based on the model predictive control, so that we are going to be able to test model-based control strategies. We are going to be able to apply a predictive management, and we would like to also be able to formulate a single objective optimization problem in order to avoid this MPC weighting factors tuning challenge that sometimes may become a difficult task. So, regarding the cell model that we use for this analysis, we have the equivalent circuit model, equivalent circuit models that are nowadays the most extended one, together with the semi-empirical aging models. Then we also have the physics-based models, the one that we have been talking about during the morning, and the data-driven models that are gaining momentum with the increase in the use of machine learning solutions. So, taking into account the three different options, in my case at least, and the ones that we are working with these modular battery topologies, we consider that the model right now is not our focus, so we decided to be more conservative, and we are working with equivalent circuit models. So, our model nowadays is the one developed by Michael Schimpf at Technical University of Munich, that is based on an open circuit voltage with a serial, with a resistance in series that can vary depending on that varies depending on the state of charge, temperature, and if we are charging or discharging the battery. Then we have the thermal model, where we assume an homogeneous distribution of the temperature, and we are only taking into account the power, the heat dissipated to the ambient. And then we have the aging model that is distributed between the calendar aging, where it especially struggles at high temperatures and high state of charge values, and the cycling aging, where we have to take into account operation not only at high temperatures, but as well at low temperatures, and paying special attention to low temperatures, but at high state of charge values. So, after defining the battery aging model, it is also important to take into account the cost related to these batteries. So, in many cases in the literature, people does not consider directly this economic cost. They just use weighting factors in order to prioritize one variable or another related to the battery system, and at the end of the simulation, they just do the techno-economic analysis. But there are other few studies that they started to consider a relation between the capacity loss and the full equivalent cycles and the initial investment that these batteries demand. So, in this case, as the model that we have chosen is based on capacity loss, we are going to establish a linear relation between the operating capacity loss, or the aging rate that we are having, and the initial investment that we have to do. So regarding the control problem formulation, we took as a baseline the case study where all the modules have a certain capacity and the power, the power shared by each of the modules is defined by their nominal capacity. So that we are able to, this way, to determine the power sharing factor that has to be shared, that has to be supplied. But then we formulated a new control strategy that we called adaptive MPC. Here you can see that there are many equations, but the most important one is this one, that is the general cost function that has to be minimized, where we are able to compute, or we are able to minimize the operating cost, but from an economical point of view, related to the battery. So that if we are able to calculate the aging rate of the battery at each time step, and then we can relate this battery aging rate with the cost, we can be able to minimize this cost function in a specified prediction horizon in order to determine which is the power sharing factor for each module. Here it is important to take into account that this weighting factor that appears here, it's something that we included in order to be able to solve correctly the optimization problem that we are formulating. And to better understand this, we did a previous analysis. Okay, so this is the rate-based integral approach for calculating the aging of the battery, where there is a sublinear dynamic related to this integral. So depending on the aging rate, depending on which lifetime stage we are operating, the aging rate will be totally different, and this may affect the optimization problem that we have to solve. So this is something to take into account, because if the aging rate is below the tolerance of the solver, the optimization will not be able to give us the correct operating point. So to better understand how this adaptive factor operates and which is the result that we are getting, we did a first approach in a residential application where we have a battery connected to the grid and with a solar generation system. So the static MPC doesn't present any kind of weighting factor, not for the cost related to the grid in this case, and not for the cost related to the battery. And in the adaptive MPC, in this case, we have the weighting factor related to the cost of the battery. And in order not to change the cost relation between the cost from the grid and the cost of the battery, we just use the same adaptive factor. So here you can see the difference between the results that we obtain. When we don't use this adaptive factor, the result that we are getting in power share or in the power delivered by the battery doesn't really make sense, because there is an unstable operation of the battery. If we are not predicting that there is a kind of demand from the household or from the residential application, we don't have to charge the battery. However, here we can just see the opposite operation. However, if we include this adaptive factor, the problem is re-scaled and the solver is able to optimize the performance of the battery, charging the battery or discharging the battery when it's really needed. Then we can see also the impact of this adaptive MPC also in the state of charge value, where we charge the battery when we don't really need it. And here in the adaptive MPC, we can see the improvement, because if we don't need the battery, the state of charge is at the minimum value that the MPC established. So now that we know how more or less the adaptive MPC works, let's have a look at the simulation results that we obtained, but applying this adaptive MPC at the modular configuration. So if we consider a scenario where all the modules are balanced so that they are exactly the same, the power is shared equally in the baseline control strategy, that it was a capacity-aware control strategy, and in the or with the adaptive MPC control solution. So then, if we have a look at, if the power is shared equally, and if we have a look at the state of charge, then the evolution of the state of charge is exactly equal. and the evolution is always balanced. From an aging rate point of view, again, everything operates exactly in the same way. And when it comes to cost, we can see that there is a minimum difference, the cost is equal, let's say. There is a slight very little difference that this is related with the soft constraint that we have to apply in order to be able to somehow reduce the difficulty of the optimization problem. But at the end, the results that we are obtaining are almost or exactly the same. However, then we extended this analysis to different lifetime stages and different operating temperature conditions, and we have seen that for a prediction horizon of 2, we were always getting the same result with the baseline and with the adaptive MPC. So this means that when the batteries are balanced, the optimal way for operating the batteries is just sharing power equally between them. Then we extended the prediction horizon, and we have seen again that the way of operating the batteries in an optimal way is just keeping the power, sharing the power equally between the 3 modules that we have considered in this analysis. But if we move to a scenario where the batteries are aged in different ways, in this case considering that 2 of the modules are already degraded and the third one is a new one, we have seen that sharing the power equally as the baseline controller strategy does is not the optimal solution. If you have a look at the power, how the power is shared during the charge, we can see that in this case, the old batteries, the green one, are charged with a higher power than the new one, in this case, the blue line. So this means that we are somehow, the aging rate is lower if we operate the batteries at the same power when the batteries are old. So the controller strategy decides to increase the power of the old batteries and decrease the power delivered by the new battery in order to look for a balance from an aging rate point of view, and then also from the cost point of view. So then, if we have a look also at the discharge, here we first prioritize the discharge of the old batteries in order to minimize the cost, but once that we are not able to supply more power with the old batteries, we have to supply the rest of the energy with the new one, so that we can struggle them from efficiency, because we have not been able to predict how much energy the system have to supply at the end of the cycle. So this black peak is related to the energy that the system somehow has transformed, has not been able to deliver to the application. From a state of charge point of view, here you can see the impact of sharing the power in an equal way between the different modules. And from an aging rate point of view, it is interesting to analyze that while the control system is able to prioritize the use of the old batteries, the blue line that represents the adaptive MPC aging rate is below the one that is related to the baseline controller strategy. However, once that the old batteries are fully discharged and we have to use the new battery, the aging rate will become higher than with the baseline controller strategy. So if we analyze this from a cost point of view, what we obtain at the end is that we are able to, at least in this case study, to reduce the cost up to 3%. If we have a look at a more extended analysis with a prediction horizon of 2 at different lifetime stages and different temperature conditions, what we have seen is that using this adaptive MPC gives us, in almost all the cases, better results from an economical point of view in comparison with this capacity-aware controller strategy from the baseline. If we extend this analysis to a prediction horizon of 5 steps, what we have seen is that the results that we are getting are similar to the previous one, so that the prediction horizon does not improve from the economical cost, but we are still getting at least better results with the adaptive MPC. So then we extend this analysis even more to some other unbalanced situations, like creating differences in cost, in temperature, or in capacity. And we have seen that we are not going to get worst economical result in any of the cases. It is possible to find an equal power distribution between the modules, and in these cases, we will suffer from an efficiency point of view, but we will be able always to adapt our battery system to any condition. And then just a comment about the prediction horizon, because here we have seen that at least this control strategy in this case study at the moment does not improve. I mean, when we enlarge this prediction horizon and when we consider more steps to the future. So, having analyzed all this modular structure with this control strategy, we have defined some conclusions, some of them related to battery architecture, where we have seen that modular topologies enable scalable designs. We can also include fault tolerance strategies. We can somehow apply new control solutions, and they facilitate the adoption of second life batteries. Of course, taking into account that we have to include more power converters than in a conventional solution, and that the design complexity also increases. From a control point of view, we have seen that the model predictive control enables advanced management solutions so that we are able to adapt to the incoming operating scenarios always in an optimal way, and being always aware also about the aging rate of the battery. But again, we have to take into account that we will have a higher computational load, and that tuning the MPC is not always that easy. And regarding the variable that we consider for the optimization, using the cost allows us formulating a single objective optimization problem so that we can avoid the use of the weighting factors, and we just directly optimize the techno-economic performance of the battery. Of course, this is totally dependent on the accuracy of the battery model that we are using. Regarding the futures line that we have defined, we are currently building up, and we are finishing just building up our battery prototype. And during summer, we will do our first test in order to be able to validate the power management solution that I have presented, and also some functionalities related to the modular battery, such as the scalability or fault tolerance. And we would like also to perform a techno-economic assessment, because industry is really interested in analyzing this aspect of modular batteries in order to know if it is worth or not just applying these solutions. And from a control point of view, we have seen that MPC combined with battery aging models presents potential for modular battery solutions. But here we would like to update our control architecture from a centralized solution to a non-centralized architecture. We have to consider also that here the power converter system or at least from the control design point of view, the power converter was assumed to be ideal, but there is still some research to do related to the efficiency and voltage amplification, so that maybe another topology, another power converter topology that is not the dual active bridge that we are considering right now, may be a better option. And then regarding the battery model and the system model that we have considered, right now the control strategy is only tested and analyzed using or considering modules in parallel, but in the future we would like to extend the analysis to matrix extractor battery topologies. And after seeing the potential of the physics-based models, in the future we would like also to update these equivalent circuit models and the semi-empirical aging model to the ones that Iker presented before. So that's all, and thank you for your attention.
So thank you very much, Xavi. Very interesting. Now you see what we research here. And now it's time for the questions. So if you have any question, you are free to ask. Okay. There's no questions? One there, okay. You can ask if you want.
Hi. Congratulations on your presentation, first of all. I was curious about the topology for the converter you used. So I see you decide to use a dual active bridge. There's a reason for that, or have you explored more converters?
So thank you for the question. I'm not the expert on power converters. There is another PhD student, Manesh Aispuru, that is working on that. But as we have seen that parallelization of the modules somehow enables to test more functionalities related to the modular configuration, and that in many applications using a higher voltage value than the one that is directly defined at the module level, it's necessary. We just decided to use this configuration in order to be able to scale up the voltage to the level that we need, but always enabling this to test at least new control strategies, or to apply new or to take into account new functionalities that modular batteries, especially the ones that are parallelized, may introduce.
Okay. Thank you.
Okay. Here you have.
Thank you. Well, I think I asked almost all my questions yesterday during your great defense. One more, Xavi, you can take it.
Okay, the last one.
The last one, okay. Yesterday and today you have been talking about these applications in energy storage systems, stationary systems. But I would like to ask, what is your opinion about the potential to apply these ideas to electric vehicles? Because at the end of the day, well, an electric vehicle, when this park, is a similar thing than an energy storage system, and you have a station similar to a modular system. Do you have any thoughts on that, or about the potential applicability of your work to this area?
So I don't have many information related to electromobility, because I think that the first application adopting these kind of solutions probably will be the ones related to generated distribution, or the ones that are similar. But taking into account that most of the batteries from the electric vehicles, as you said, are based on a modular concept, even if this is then scaled up to the requirements of the application, maybe it could be this an interesting option in order to, in case of a failure of the battery, not to change the whole system, and this way update just a single module, avoiding somehow spending more money repairing the battery system, so that it's going to be a more reliable solution for the user, because at the end, if there is a failure and because of one module we have to change everything, the people will not want to spend all this money.
Yes, yes. That is one possibility, and maybe for heavy vehicles can be a possibility, certainly. But I was thinking more about the possibility of considering each single vehicle like one battery module connected to a DC grid, and the DC grid is a charge station. So, do you know what I mean? Like one vehicle is like one module of your battery here, and the charger basically is your dual half-bridge converter or dual full bridge or whatever. Anyway, maybe we can talk about this later. But
Okay.
yes.
Okay.
But I was just thinking that the concept of modularity can be basically applied to multiple electric vehicles, treated each battery in one vehicle as one module of a battery.
Yeah, with the concept to vehicle to grid and in an energy community. And
yes.
Yeah, so yeah, definitely we can consider also each battery of the, I mean, we can consider an electric vehicle to be just one module connected to the grid. So taking into account that each of the electric vehicle may be at different conditions, this kind of solution or this kind of control strategies may be a good choice in order to manage these electric vehicles in an appropriate way, not to age them too much, but in order to take benefit from each of the batteries.
Okay, thank you.
You're welcome.
Okay. Is there any other question? Okay, so let's move on. Thank you very much, Xavi.
Thank you so much, Eric.
And now the last talk will be in charge of Eric Scholz from Aalborg University. He's going to talk us about battery state of health estimation in real life conditions. Eric Scholz received his master's and PhD degrees in electrical engineering from the Department of Energy at Aalborg University in Denmark in 2005 and 2010 respectively. From 2009 to 2012, he has been an assistant professor, and since 2012 he has been an associate professor there, both positions also in the Department of Energy at Aalborg University. At the department, he is the leader of the research group in e-mobility and drives, and the vice leader of the batteries research group. His research interests include the usage of power electronics, electric drives, fuel cells, batteries, ultracapacitors, as powertrain in various applications like electric vehicles, industrial machinery, and heavy-duty systems. In addition, he is also focused on battery state estimation, electric and thermal management, and modeling of battery cells and packs. He is also active in power electronic converters and their integration for fuel cell, electrolysis, and power-to-X applications. So, Eric, the floor is yours.
Thank you. Yeah. Thank you for the kind introduction, and thank you for inviting me. I'm very honored to be invited to this great place. So, yeah, I will talk about the battery state of health estimation. So it's an area we have been working on in several projects, so I will present some of the results from those projects. And then, like many others, I think in this room, I'm also electric engineer background, so we have a lot of focus on, we are very applied, so we think for us it's important that you also work in out of the laboratory, so that's why I add this real life conditions to the title. Yeah, I'm from Aalborg University, so those of you who are not so familiar with the Denmark, then it's located here in the west part of the country. We also have a small branch in the capital, Copenhagen, and also in the city of Esbjerg. So we are a little more than 2,000 students in total. And we are a university which cover many disciplines, so we both have social science and humanities, medicine and technology, and then also engineering, which the faculty I'm from. Yes, but I will talk about the state of health. First, I will talk about some definitions. Professor Timbolo, you mentioned that it's not very defined, and I agree with that. And also come into what is the purpose of health estimation? Why do we need that? Then I focus on two estimation fields, so power estimation and then the capacity estimation. Where the capacity, I will go through 4 different methods we have been working on, and then finally the summary. But just to make sure we have a common ground, earlier today we have seen similar figures like that. And I would also like, Jorge, you make an analogy to cars. So I think the state of charge can be seen as somehow the fuel gauge. So is the tank empty or is it fuel? And then the health, that can be seen as the total size of the tank. But then what happens with batteries or cars, the tank will somehow shrink over time. So you can put less fuel in it as time goes on. So this is illustrated with this health. So when the battery is new, you can use that much. But then as it degrades, you can use less. So that was from capacity point of view, but then we also have the power, which is also depending on the application. Could be a parameter you want to control and estimate. So the state of power simply just means the available power you have available for a certain amount of time. So that means that if you have so state of health, that's somehow a parameter which is important for the user. So 100% health means that the battery is fresh, and then 0% means the battery is completely dead, cannot be used. But there are also more definitions to the health. Probably the one often used is the capacity base. So you would define it as the actual capacity you have compared to when the battery was new. But it could also be defined in terms of energy. So the energy you have available compared to when the battery was new. Or the power, again, the power you have available compared to when it was new. But speaking about the power, if we look at a very simple electric circuit diagram, what limits the current is this resistor. So how much current we can draw from the battery depends on how deep we allow the battery voltage to go. And if you look at the data sheet of a battery, there's an upper limit and then a lower limit, so we need to stay within those intervals. But if you then calculate the power by these two equations from the actual power, so this is given by the actual resistance, and then compare that to the beginning of life power given by the beginning of life resistance, then it turned out that the power state of power can also be expressed as the beginning of life resistance or the actual resistance. But speaking about the health, it's a little bit comparing banana and apples if you don't know the frame. Because if you should estimate the health, then you really need to determine how should the test be done. So what voltage range are we talking about? At what current level are we talking about? And what temperature should the test be done on in order for you to estimate the health? And to some degree, I think this term state of health is not common accepted neither in layman speaking nor in the academic community. And also, many EV manufacturers they also use the word health in the PR material. So this is from something I took from the website of a Hyundai Ioniq 5. This car here. Sorry for the Danish text, but they give a warranty for the car. They get either 8 years or 160 kilometers, and then they say the state of health should be below 70%. But what does 70% state of health means? Is it capacity or energy? And which test do you need to do in order to find out whether the car can do this as the promise? So I think there's a need to have more clear definitions which is common accepted, or at least then it should be clear from the material what kind of test should you do in order to verify if this number can be achieved or not. So why do we need to know the health? One of application could be, for example, a car. I mean, if you drive in a highway, it's pretty important that you know that you end up on the final destination or not. Or if you have grid storage applications, can you then deliver the power to the grid as you promised to do? Because if you look at a battery model like this, it includes some electric parts, some thermal part, but all the parameters of a model depend on the health. So in order to assess whether the battery can do its task, then we need to know the health. And also, if you want to predict if you have a given application, how much time in the future can you use this battery? So this is what we call remaining use for life. You also need to know where are the battery on its life curve in order to estimate how much longer time can you use the battery. But in many applications, you cannot measure the capacity of power, because of course that will just be the easiest things to do, because if you can just measure the capacity, then there's no reason to estimate it. But as I said, many applications, you don't have the luxury to do that, so you cannot bring the battery to the specified test condition to actually know the total power or capacity. So therefore, we need to develop some methods so we can estimate the health in a relative easy and fast way. So this figure shows how that can be done. So the health can be determined in several ways. So either by doing some experiment, which can where we extract some parameters, because in many applications they try to map some kind of a feature point with the health, and then this feature point can be obtained by some experiment or based on the outcome of some models. And then what combined is a model, so that could be machine learning methods or also other simple models. So basically state of health estimation is about identifying some feature points and then do a model to make this relationship. Yeah, but then first I'll talk a little about power estimation. So that was a project we had some years ago. So why do we need to know the power? So I think Jorge explained very clearly that BMS has an important task. It should make sure that the system is safe. So if you have a battery, it needs to operate within a very small limit of the voltage and also temperature. So the BMS is the brain of the system, so that needs to tell the rest of the system how much power or current you can draw in order to be sure you don't exceeding the limits here. So that means if you have electric vehicle applications, that could be doing acceleration or braking. You need to tell the inverters how much power that they can take or deliver to the battery. So if you have a relative simple model, then it's what is determine how much current you can draw. This is simply given by the resistance. Here is divided into a discharge resistance and charging resistance. And then you simply calculate how much current can I draw in order not to exceed the upper limit or the lower limit. And of course, this value will change depending on where you are on the voltage curve. Then you can calculate how much power you can draw. But this is, of course, the real world doesn't look like this. In real world, you have dynamics, which can be modeled with some RC circuit elements. So therefore, you also need to take the time into to account. So the power you can draw depends on how long time you want to be able to draw this power or deliver this power. So therefore, we actually, in order to be able to estimate the maximum power, we need to estimate these electric circuit parameters, and that can be done, for example, by a Kalman filter, extended Kalman filter. Then you can get the dynamic parameters of the battery, and then by doing converting the differential equation to Laplace and then solve in time domain, you get some exponential first order equations here, and then you can calculate how much current can you actually either draw or deliver to the battery in a certain arm of time. So that can be implemented in the BMS, and this is what we see here. So here we have a battery which has been exposed to its emission profile. And then what the BMS does, it always calculates the maximum current, either positive or negative, which can be drawn or delivered to the battery. And then we see the voltage boundaries and also the power profile here. Yes. So that was just the example how it looks like when it's implemented. Then the BMS is always estimating the maximum current that the rest of the system can use, and then that information is passed on to the inverters of the motors. Yes, so that was power estimation. Now we'll go on to capacity estimation. So capacity estimation is often done in two ways. Either if you look at the voltage curve, you can see there's somehow a good relationship between the voltage and then how discharged the battery is. So this information somehow maybe could be used to estimate what is the total capacity. But other methods, they seek to identify some kind of a feature point which then can be used to estimate the capacity, which I'll go into later. Here, in this project, we are trying to develop an online method for capacity estimation. So this method we developed here, that actually is where we used the first principle. Because if you look at the voltage curve of the battery, a function of a state of charge, then we can see very clearly that if we know the state of charge, or we know if the voltage is a given point of state of charge, then we know the change in state of charge. And then if you also integrate current, then we know how much amp hours have been passed in this interval. So that means that the total capacity can be calculated by this simple equation, where we simply just find two different state of charge values and then divide that up into the capacity which has passed in between. But also calculate the capacity, then we also need to include some compensation factors by this in this integral equation here. So we need to compensate for the actual temperature or the current level. So we have done a mapping of the battery where we measure the capacity for different temperatures and different C rates, and then we can introduce this compensation factor here when we do the capacity calculation. So that means that we have two ways to estimate the charge, either by current integration or by open circuit voltage measurement. So the method we have proposed here is actually very simple. So it works in this way, that when the battery is active, being used, either charging or discharging, we simply just do current integration. But then when the battery is doing nothing, then we simply just measure the open circuit voltage. And then because we have done this open circuit voltage mapping in the laboratory, then we know the change in the state of charge. And then we can calculate the total capacity by this simple equation I showed here. But then as the battery or time goes on, the battery will be age. So we should not include all calculations. We somehow have a moving window where we only use the latest results. That's why we have this recursive least squares filter, which then will give off the state of health. And then this capacity we estimate that is also used for the state of charge calculation up here. So it's somehow, so both the state of charge and the state of health somehow bites themselves in the tail. They both depend on each other. So here we try to verify the method by a WLTP profile, and we do that for different temperature levels, because you cannot be sure that you have the same temperature in real life all the time. So that's why we try to do it for different temperatures. And we can clearly see that if you compare just with the Coulomb counting, then Coulomb counting will somehow drift as time passes. Because if you just have a very small error in the current sensor, that will give that error will accumulate over time. So therefore, when we have this combination of the open circuit voltage measurement and Coulomb counting, we can have a quite low error, which this graph is trying to illustrate. Yes, so that was the state of charge. Then we also have the health part, the total capacity. So here we try to apply the method at different temperatures, so at 35 degrees, 25 degrees, and 15 degrees. And then we try with different initial guesses, and then we want to investigate if the algorithm converts to the right value. So the right value is the one given by the dashed lines here, and then we can see over time the algorithm converts to almost the right value. But of course, it's not fast. It takes more than 100 hours. But you can also say that for still health estimation, it's not something you need to estimate each second, minute, hour. It's because it doesn't change so fast. Yes, then move on to another project we had called Batnostic. And this project was actually industrial driven because it was invented for this project was invented for the second-hand market. So the idea was somehow that if now we have a lot of electric vehicles on the market, and in some years there will start to be a second-hand market for electric vehicles. But then the problem is that if you, as a potential buyer of a second-hand electric EV, do you really then you're really concerned about the health of the battery, because you don't want to end up in a situation where you buy a second-hand EV, and then a few months later you have to bring it to the workshop and buy a new battery pack, because the battery is the most expensive of the car. So therefore, we want to. The purpose was to develop some method to estimate the health, the condition of the battery, and that should also be. The method should be fast. That was one condition, but then it should also be independent of the car manufacturer. So we did not want to rely on the information the car manufacturers provide, because, as I said before, the health definition is not really clearly defined, and we also have a hypothesis that the car manufacturers maybe will expand the voltage window you can use for the car. So that could be one way to overcome the degradation, because if they just expand how much voltage you can use, then as a user point of view, you experience the same range until one point where they cannot expand the window anymore. And then you'll see a huge drop in capacity maybe. So at least that was a hypothesis that we had. So that's why we want to develop a method which should be independent of any information from the car. So that was somehow the background of this project. So the idea was that when you have a car being charged, then if you have enough cars being charged, then you can start making a model. So this basically will be data during modeling. But we did not have a lot of cars. We did not have a lot of data. So therefore, in order to develop the method, then we based our research on testing laboratory on cell level. So we tested a Nissan electric EV and then a BMW i3. And then we bought spare modules for both cars. So here you see a spare module of the BMW i3. So that consists of 12 cells in one module. So we bought one of those, and then we took the module apart so we can test the cells individually in the laboratory. Because then when we have done all the tests in the laboratory, developed the method, it could be applied at vehicle level, and this is what you see here is a picture from one of the project meetings where we have a charger which we then can control. So we can control the charging current, and then we can apply the method to the vehicle. Yes, but we want, it's important for the method that it should be independent on how the cell have been aged, because we do not know the history of the car, and we for sure do not have any physical model of the car, because we don't want to rely on any information from the car. So we try to test the cells in many different conditions we could imagine the car will be exposed to real life. So we did these test matrix. We tested for different both calendar engine and cycle engine, where we did it for different temperatures and different state of charge level, and also different C rates. And then we investigated two methods. One method is a partial charging method. And what does partial charging method means? Yeah, so the basic idea is that if you define a voltage window where you have an upper voltage and then a lower voltage, then in this interval there will be some amp hours if you charge the battery, but that will evolve over time. So what we see here is two curves. The blue one is a fresh cell. So within this voltage interval, there is a certain capacity. And then in the red one is an aged cell. So in the same voltage interval, there is a smaller capacity. So we want to investigate, is this, you might be surprised, it's a very, very simple method. Can that be used as a way to estimate the total capacity? But then the question is, what window size should we use? Of course, the wider window, the more accurate, but it should also have a commercial value. It should work in a workshop, should not take too long time. So it's a trade-off about accuracy and then how fast the method will be. So we need to demonstrate that there's a relationship between the charging capacity and the discharge capacity, because we can only have access to the battery during charging, but the battery is doing its job doing discharging, so that will be the first thing we need to prove. And then we also need to prove that this partial capacity has a good relation to the total capacity of the car. So this is what we investigated. So the first thing is the Coulombic efficiency. So what you see here on the x-axis is the discharge capacity, and then we have the charging capacity on the y-axis. And then we also can calibrate the Coulombic efficiency, and that is close to 100%. So that means that the first assumption considered as good enough. We can assume that the charging capacity is almost the same as the discharge capacity. Then the next thing is to demonstrate that this partial capacity also you can model that, use that for the model of the full capacity. So I'll skip this slide. Yeah. So what we did here was to try many different combinations of the lower voltage and then the upper voltage, then just simply to see how good is this estimation. So what you see here is the root mean square error, depending on these voltage interval. And then, of course, the wider voltage window you use, the better accuracy, and the smaller, the lower accuracy. But we find out that if you use a window of 3.55 and 3.8, we find that was a good compromise between the time it will take and then the accuracy. Then if you use this as a model, we can see that the estimations fits very well to the measured values. So where we get a root mean square error of 1.8%, which I think is acceptable, but it's not a perfect method, because some few points we get a maximum error of up to 6%. But at least it's a very, very simple method. Then another method we also develop in the same project is based on the concept called incremental capacity analysis. So what is this? If you look at the charging voltage of battery, when it's been charged with constant current, you see the voltage will rise until you have to shift to constant voltage charging, then the current will reduce. The charging capacity is simply the integral of the current. So if you then plot the charging capacity as function of the voltage, opposite. If you plot the charging capacity as function of voltage, then you'll get this curve. What this incremental capacity method is about is to take the derivative of this curve here. So if you differentiate this curve, then you'll end up with a curve down here. And then you can see there's many peaks illustrated with red circles, and also there are some valleys with green circles. So that means that we have a clear signature of the battery. So this is our feature point. So we want to see if we can make a model with these feature points or peaks and valleys, and then the total capacity of the battery. As you see here in one of this paper, where we have a battery exposed to calendar aging. So this is from beginning of life after to 1 year almost, and then we can see how the valley evolves over time. And then if you plot the capacity fade as function of this voltage change, the position of the valley, we can see there's a quite good relationship, just a first order polynomial. So it's actually a very, very simple model. And and we like this approach because that's something we very easy can implement in the laboratory when we want to charge vehicles, because we can control the charging current. But when we started the project, we had a lot of concerns applying this on car level. One concern is that in the battery pack you have some components between the charging port and then the battery. There are some fuses, relays, cables, connectors, and so on. Will they destroy the method? And also the temperature we really cannot control. That's not up to us. The control is as it is. And also the method should be fast, because in a workshop they need to have a car in, do the job, and then out again. So it should not take too long to time. So how fast can this method be? And also we are concerned about if there will be any cell-to-cell variations, because we can only measure the pack voltage. We don't have access to each cell voltage. So just to illustrate this point, we did a test on a homemade battery pack. So this is our lithium iron phosphate, and what you see here is the charging capacity function of voltage for each cell, and then you can see the cells are not the same. So it actually is a very bad pack, but it was also homemade. So that means that when we do this ICA analysis, we'll get many different peaks, which are scattered around. But when we do measurement on pack level, we can only get the average of all curves together, not individual. So that would be a limitation of the method. Yeah, but we tried to, so the same data we use for this partial charging method, we also applied to this method. Then we did the ICA calculation, and then we can see this is one cell stored at 35 degrees Celsius at 50% of charge. Then we can see how the capacity decreases. So this line here is the beginning of life, and then this curve here is from month 17. So we can see there's an evolution, but then when we do the ICA calculation, we get the curves here, and then we plot the peaks and values, and we can also see there is some evolution of the peaks. For example, this peaks 1 go down, and we have peak 2 here go horizontal, and so on. But in order for this method to be useful, it's important that the peaks, they should evolve in the same way, independent on how the cell have been aged. So that's why we tested different aging conditions. So this was these conditions here. Then we have also two other conditions. And then we realized that for this particular condition, 45 degree, 50% state of charge, which is quite a high temperature, we're starting having actually a new peak, which was a valley which was present for the other conditions. And also we noticed that when you tested two other cells and other conditions, so 10% state of charge and 90% state of charge, we actually noticed that this peak 2, if you see that, if you go one back, you see for the other condition it was horizontal, but now the behavior seems to go more upwards. So that means that if this peak 2 should be used, it will not be very good because it somehow depends on how the cell have been aged. So at least this IC coordinate of peak 2 will not be a good indicator. Yeah, and then the last one, that was at very low temperature, so there was almost no degradation. So that was on cell level. Now we need to move to car level to see if the method can be applied there. So we tested two different BMW cars. So first we want to test it for consistency. So if we repeat the test, we didn't get the same result. And then the results we get on cell level, can they be transferred to the car level? So we put the cars inside the garage and then have set the temperature so it was settled overnight, so we're sure that what the temperature was. So what you see here is the result of those two cars, and we can see that they have somehow the same shape, but this so that means the method is somehow consistent. But we also know that for this EV2, the second car, we lose this peak 3 and valley 3. That simply is simply not present for the other car. So that means that that car is a bit different. So it would be a very bad idea to do a model which is based on peak 3 and this valley 3, but because it simply disappears at some point. So we need to look for some other valleys or peaks. But in order for the method to work, it's important that the location of the peaks and valleys do not change on how the battery has been aged, as said before. So this map actually shows the coordinates of the peaks and valleys for where both the cars and cells have the same capacity. So we see that the peaks and valleys are somehow in the same area. Because they should also be detectable, and we apply the algorithm, we need to know if we identify a peak, where does it belong to? Is it peak 1 or peak 2 or whatever it is? So that's what this figure shows. But then we simply try to plot the coordinate of the peak and valleys as function of this partial charging, just to see which peak and valley give good results. And then it turned out that this peak 2 here, the voltage coordinate, so that means it actually was here. So the voltage coordinate of this peak 2 here actually turns out to give the best trend. So if you plot the partial charging capacity as function of the voltage coordinate, you have almost a linear relationship, which can be modeled by a very simple first-order polynomial equation, which is nice, I think. Yeah, so we try to apply the method and estimate the health. Then we see we get a linear relationship between the partial charging and then the health of the capacity. And we do that both on the cell level and then also on car level. That's the blue ones here. So yeah, so I think the method works quite fine. But then, as I said, it should also be applied in real life. It should be applied in a workshop. So the workshop guys, they were not happy that we said that the car should be brought in the day before, and then it should acclimate the whole night to have a certain temperature, and then you can do the test. That was not good enough for them. They want a car fast in, and then they do the test, and then it goes out again. So we try to, luckily get funding for an extension of the project where we then want to be able to compensate for the temperature. So the idea is that if a car comes in, you don't know the temperature of the battery pack, but you still need to have a method which can estimate the capacity. So that we tried in this project. So what you see here is again these ICA curves, but this is done for 4 different C rates, because another thing, as I said, is the speed of the method, how fast it is. So the higher current, the better, because the faster it is. But then the penalty is that when you increase the current, these peaks and valleys, they somehow start blurring out and fading out. They're not so clear anymore. But how current can you go? This was an open question. And we also see the temperature. This is illustrated by the color figures. The temperature also will influence the coordinates of these peaks and valleys. So basically the idea was to try to map the evolution of these peaks and valleys during the age. So again, we did some tests at cell level. So this, what you see here, is the result of a cell being stored at 45 degrees Celsius, 90% state of charge. So here you see the evolution of the ICA curves during its life. So the blue color is 100% health, and then the yellow color is 70% health. And this is done for different temperatures, so 10 degrees here on the right column, 25 in the middle, and 35 to the right. And then we also have 3 different C rates, so 0.2 C in the top, half C in the middle, and then almost 1 C at the lower. So the equipment could not go higher than the 0.87, so that's why we did not use 1C for this test. But then we take these results and then try to do the same thing as before. We try to see, can we make a model which somehow maps the coordinate of these peaks and valleys to the capacity. And we do that for the different temperatures and different C rates. And then we can see at least for the 25 degrees Celsius and 35 degrees Celsius, there's a not perfect match, but at least some good trends, so that can be used as part of the model. Whereas the 10 degrees did not really show promising results, unfortunately. Yes, so that was 2, I think, very practical methods. But in order to have the method even faster, we also want to try to investigate it, if the impedance itself can be used as the method. So many people use impedance spectroscopy to make electric circle models, as we see one example here. So if you get the impedance, where you simply measure the impedance for different frequency, then you can use that to extract the circuit models. But this is they can be difficult, and especially in a car where you don't have that much processing power or memory. So we want to investigate if we somehow can skip this modeling part, if we directly can take the raw impedance measurement and then map those to the capacity of the battery. So. So that is the hypothesis that we want to investigate, whether we can take these impedance data for different health conditions at different, and then at different frequency, try to make this establish this mapping. So he had a student who did this for his master project. So what he did was that he developed a machine model where he took 7 impedance data for different frequencies, 7 between 10 Hertz to 1,000 Hertz. And then he was applying that to his machine model. And then so he used some data for training and then some for verification. But it actually turned out that the root mean square error was quite okay. So it was below at least 3% was the highest, but also was below down to 1.5% for different state of charge value. So we think as some is. Then, of course, you can say, is this really real life? Because isn't it difficult to do impedance spectroscopy in real life? And yes, that is true. But I think there are some methods where you can inject some signals where you only get parts of the frequency, because we don't need to do the full impedance map. We only need to get the impedance at selected frequencies, and I think that should be possible in given application. Of course, if you have some control of the hardware. Yeah, so I reached the end of my presentation. So we have talked about state of health. So this is usually defined with respect to either capacity or power. And the state of health information is important because it basically tells you if the battery can do its job or not. Then we talk about maximum power estimation, so that this is something which is dynamic because it depends where you are on the charging curve. So we need to estimate the impedance also to be able to estimate how much power we can draw for a given amount of time. Then we also talk about different methods to estimate capacity. And you're probably surprised how simple the methods are. It's just linear equations, basically first order polynomials. So we try to investigate partial charging, incremental capacity, and also impedance. So this is what I will call offline methods, where you need to do a lot of testing and mapping in the lab beforehand, and then you do the modeling and apply it afterwards. Whereas the recursive method here, this is an online method which works on the fly, so it's adaptable, so we'll adapt to the new situation. And here you still need to do some kind of pre-mapping. You still need to have the map of the capacity as function of temperature and current, and you need to do the open circuit voltage mapping. But that's it. The rest you don't need. So I think that's an advantage by this method. So yeah, but thank you for your attention, for listening to me.
Thank you very much, Dr. Scholz. Very nice results, very interesting. And now, if you have any question, yeah.
Hello, and thank you for your talk. My question is simple. Have you think about maybe using active learning methods to reduce the amount of data that you need to collect in order to have good estimates of this SOH?
You say active learning?
Yeah, so instead of testing, maybe it doesn't make sense, the question. Instead of testing at pre-selected conditions, you kind of make a more data-based guess on which should be your next observation, so that you reduce the amount of tests that you need to make overall.
Yeah, it is not a method I'm familiar with, but I think I understand the value of that method, because I think it's a problem in the field of battery, that you need to have a lot of resources. You need a lot of channels, climatic chambers in the lab, and do a lot of testing. And then 1 year after, there's a new generation, and then you can start all over. So I think it's, so there exists some methods which can do that, which can reduce this pre-training. I think that will be very much appreciated. Or if you have a lot of data, that actually was the purpose of this diagnostic project. So the idea is that if you can have access to the charging data each time a car is being charged, I think you can also use that to generate some models. Because that's something that needs to be done anyway. Whereas the testing in the lab, you only do it for the sake of doing a model. But good point. Thank you.
Yeah, there's another question there. Okay.
Hi, congratulations on the presentation. It was very interesting, and I took note of some of the references, so I will be reading your work. I have one question, well, a couple of questions actually, regarding the recursive algorithm.
Yes.
So, if I understood it correctly, you need the battery to be idle in some of the periods of time to be able to obtain the difference in state of charge based on voltage, I think.
Yes.
Would this method be applicable if we are considering an application where the battery does not rest idle?
Oh. Yeah. So you can repeat the last part.
Yeah, sorry. Yeah, would this method be valid if we are considering an application where the battery does not rest idle?
Yeah, I think that would be the limitation of this particular method. Okay. But I think maybe time also will evolve because when we started the project, it was our impression that BMS manufacturers does not want complicated computation. So there was also asked this question about column counting because I think today. I think it seems to not be a problem to having a Kalman filter running in the background, which then can estimate the open circuit voltage. Mm-hmm. So you don't need to rest and wait to measure it. So I think that would be probably, if you should do that project today, probably that what we'll do. Yeah. Okay. So because that will of course be a limitation. If you don't have a rest period, then be a bad method. Mm-hmm. But for electric vehicle. A vehicle is almost being used, not being used. Most of the time, it's just standing still, doing nothing. So I think that should work fine.
Mm-hmm. Okay, thank you. And I have a second question regarding the incremental capacity analysis method. Yeah. In the first part, when you did not take into account temperature and so on, I think you established as features the coordinates of the incremental capacity peaks. But if I understood it correctly, you use the whole range of voltage, like a full charge process from minimum voltage to maximum voltage to obtain all those peaks. Would this be a valid method if I started, for example, at 50% SOC and then I charge and I only can observe the higher voltage peaks, for example? Would those coordinates be still valid to calculate this state of health?
Yeah, I would say we have not done all the conclusion of this method yet, because so there are still some open questions. The nice thing will be if you can get one peak or value, which you somehow can follow the entire voltage range and also life, but it's not sure that you can get that. So one way to improve the strategy could also be to apply more peaks and valleys depending where you are on either the voltage curve or where you are on the life of the battery. For example, what I show with this slide here, that suddenly this peak 4 and valley 4 was occurring. So that also gives some indication where are we on the life. So if you somehow can detect that could also be a part of the method. But then I think you ask about when to apply it. So the idea is that you just need to pass this peak or valley. So you don't need to do a complete charge. But of course, if you make a model based on this peak 1, and the battery is almost fully charged, then it will not be good, because then you passed this area already. Yeah.
Okay, thank you.
Okay, welcome.
Yeah, there's another question right there. Yeah, thank you.
Thanks, Eric. Really interesting presentation.
Thank you.
I was curious about the applicability, about your opinion about which kind of method would you use to calculate the state of health in a stationary application where you will not have a full charge and you will have some charge-discharge events. Yeah. And with LFP technology.
With LFP, yeah, that's tricky, because for LFP, probably this method would partial charging capacity will not work so well, because you have quite a flat voltage curve. That's a good question. We did not work with that particular problem for this technology by myself. But still, I think if you do ICA, I think you still will get some peak and valley. So I think they still could be used for that. I will assume. Yeah. So that's a little bit of no answer to your question. Sorry for that.
No, it's, I ask for your opinion, so it's wonderful. Thank you.
Cool.
Okay, is there any other question here? I think that we have another one on the chat.
Oh, okay, yes.
Well, thank you, Professor, for the nice presentation. The question actually was online, was aligned with the question just asked about LFP cells because of for the SOH estimation, because of their flat curve. You have to move out outside the typical service operational SOC values, 10 to 90%. So he was wondering about if there was any other alternative rather than moving from those 10 to 90%. But well, it's almost it's quite answered. So thank you for your question.
Yeah, we were maybe a little bit lucky that we used NMC batteries, because that was used a lot for cars, at least earlier. I know now LFP is starting appearing in cars also. So, yeah. But yeah, good research topic, I think, if there are potential PhD candidates.
Okay, if there's not any other question, we can leave it here. So thank you very much, Dr. Scholz.
Yeah, thank you.
So the event has come to the end. It has been a pleasure for all of us to have you here. Thank you very much for all the attendees and all the people that has been following the event online as well. Thank you very much for all the speakers we had today, especially to those who have traveled to be here. Thank you. In the following days, you will receive all these slides, and if you are interested in any of the researches that you saw here, just contact us and we will try to collaborate. So thank you.